Here's the live stream, right? And tell me when it starts. What is that? Okay, you can see it? Okay, good. At least that's working. Don't want to hear myself though. Okay, that's better. Okay, cool. Shall we get started? Well, welcome everyone. I guess welcome people on YouTube also, since we're live. I think it's good to actually have this lecture finally in person as well as online. I think this is my first lecture in person since last March 2020. Yeah, that's good to be in person, I guess. Hopefully we will fix this issue with science and not dogmas, but the world is in a weird situation these days. Okay, since we've covered 2 lectures, we're going to continue memory systems today. I think, guys, can people on YouTube or other place hear me well on Zoom? Normally I have those windows open in my other computers and I can see what's going on. Just make sure everything is good. And okay, yeah, if people say yes, that's good. Well, whenever they say yes, I guess we're going to see that chat window coming up. A nice feature of your Zoom interface, but Zoom is still better than many other software, I think, for this sort of collaboration, let's say. It should also go quickly, but it doesn't go quickly for some reason, as you can see. So how do I make sure it goes quickly? Okay, whatever. Hopefully it won't be so annoying. Okay, so we're going to continue with memory systems today, and I'm going to give you another broad perspective on memory systems, challenges and opportunities. Can you hear me well, by the way, because of this? Okay, as long as you can hear me well, that's good. I don't like the, these glasses and their effect, but that's okay. Okay, so we're going to talk about basically an overview of memory system challenges and opportunities, and then we're going to talk about some solution directions, and then we're going to look at some example issues in the memory system that I believe are extremely important. And then we're going to delve into a lot of really interesting issues, in my opinion, in the memory system that are being tackled today. But just to remind you, these are 4 key issues that we discussed in the first lecture. How to design fundamentally secure, reliable, safe architectures, fundamentally energy efficient, more memory-centric, data-centric architectures, low latency and predictable architectures, and architectures that are specialized to maximize efficiency and performance for different applications. And some applications are written here, but you can imagine many more clearly. And I think we're going to cover a lot of these in the course of the next 10, maybe 13 or so lectures. We'll see. Every semester is a bit different. I really want to get rid of this, but John, can you find a way of doing this? I have no idea. Do I have to look at the chat? Okay. But it really doesn't want to go away, right? Okay. Yeah, I guess when you're designing software, this is an example of how not to design software. If the user doesn't want something, don't do it, basically. I think that's a good, that's probably a very good principle in designing software. Under more button, okay. Completely hide it. Okay, can you see anything? Hide names, hide video panel. Okay. What is video? Okay, I see. Well, thank you very much. Maybe that should be the default, I don't know. Okay. Yeah. Okay, so we're talking about memory and storage. And when I talk about memory, storage is actually similar. A lot of the issues we discuss in memory is going to be similar in storage. It's going to be similar in caches also, like SRAM memory. So memory is memory in general. The technology is different, but a lot of the issues that you will encounter are similar. And you'll see that when we talk about data retention, for example, read disturb, different kind of effects. So let me give you the perspective. I think this was a little bit clear. I'm going to go through this relatively quickly, but we're going to look at why are we starting this course a lot with memory, basically. Normally, if you take a computer architecture course, people start with processors. Well, we did it in digital design and computer architecture, right? If you took it. Or if you took another computer architecture course, digital design course, you started with processors, right? You learned how instructions get executed on a pipeline, etc. I don't want to repeat it in a more advanced course, basically. Hopefully, you know all those basics. Today, computation is not the problem, basically. Today, we know how to process instructions really, really well. We are able to do pipelines, out-of-order engines, etc., extremely fast, as well as energy efficiently also. I mean, reasonably. We can always do better, of course, in both of those dimensions. But computation is really not a problem. That's why we're starting with memory. Today, we're so much bottlenecked by memory. And I'm going to give you more data showing this. And we're going to cover a lot of interesting case studies, papers, etc., that show this as well. That's why this course starts with memory. We're going to look at computation also. Of course, memory is not enough by itself, right? You cannot just store data. You should do something on the data also. So computation has to be integrated with memory. So we're going to talk about that as well, certainly. But that's why we're going to talk about memory. But let me motivate it a little bit more, basically, especially today. Memory has always been important, actually, for decades and decades. But today, we're really constrained by memory. So I'm going to give you multiple perspectives about it: performance, energy, scaling, reliability, security, some of which we touched on last time. And then we'll talk about some trends, opportunities, and challenges. And feel free to ask questions like what we have been doing over Zoom. Now, in person, you can ask more. I guess the Zoom people somehow need to ask, and somebody needs to convey me when they ask questions. Okay, so we're going to talk about memory system, and memory is general, but we're going to especially talk about the main memory part. And this is a traditional system where you have processors, main memory, and storage. This later, we're going to deconstruct the system and talk about memory and storage merging together as well with emerging non-volatile memory technologies. Can we actually have one unified system that caters to both main memory and storage needs, and maybe caching needs also? But main memory clearly is a critical component of all computing systems that we design today. Almost all computing systems use some main memory. Usually it's DRAM, server, mobile, embedded, desktop, sensor, whatever you can think of. And this must scale in many dimensions. Its capacity or size must increase, technology must scale, efficiency must increase, cost should reduce, and management algorithms should scale if you want to improve the performance, cater to the demands that we have been putting on memory through the huge improvements we've had in processing, and if you want to reap the benefits of the technology scaling going forward. So a lot of things must improve, clearly, and they have been improving, actually, but we're having difficulties now. And main memory is a fundamental component of essentially any computing system over here. You can replace these processors and caches. I guess this is not visible online. My laser pointer is probably not visible online, right? Whenever you look, so I should really do this. Processors and caches with FPGAs, GPUs, or machine learning accelerators, or a heterogeneous combination of all of those. You still have main memory, and you're usually bottlenecked by main memory in all of those systems. This is another shared resource picture of main memory, or memory in general. This is my cartoonish picture. I do this picture in about 2007 or so, when I was writing a grant proposal to the National Science Foundation in the United States, arguing that we should really look at quality of service in multi-core systems. And I mean, the picture hasn't changed, but the key thing in the picture over here is the cores are small. There are many, many components that are just dedicated to moving and storing data, right? Caches, interconnect, other caches, other interconnect, memory controllers, interconnect, main memory, interconnect, storage. So if you actually do the calculations, more than 90% of a single node area-wise is dedicated to memory structures, data storage and movement structures. And I didn't even tell you what's inside the cores, right? Cores have huge register files, usually, L1 caches, especially for the GPU core, it has huge register files, right? So most of the system is dedicated to storing and moving data today. Even then, even though the system looks like this, most of the resources are dedicated to memory. Memory is still the bottleneck. So you can imagine how bad the situation is, basically. Okay, so let me give you an overview of the state of the main memory system. Again, this is an overview talk. We're going to delve into a lot of these issues later. But recent technology, architecture, and application trends lead to new requirements from this memory system. Well, new, relatively new, let's say, because this slide is also old, by the way, from 2007 or so again. But it's relatively new in the grand scheme of history of computing, let's say, right? And they exacerbate old requirements also. Clearly, we demand a lot from memory. We're going to demand more. And DRAM, the main technology we use to build main memories with, and memory controllers, as we know them today, are unlikely to satisfy all the requirements. And we've discussed last time that RowHammer problem is actually causing problems, right? Clearly, they're not satisfying the reliability and security requirements as we're used to so far. And we'll see a lot of other requirements that they do not satisfy. And some emerging memory technologies that happen to be non-volatile enable new opportunities and satisfy some of the requirements that we place on the memory system, like scaling. They scale quite well going into the future. And they may enable opportunities like memory and storage merging together, or manipulation on persistent data from the programming language directly. Right? So these are very interesting trends. We're going to cover both of them in this course, clearly. So I think given these trends, we need to rethink the main memory system to fix the issues we're having with existing technologies and enable emerging memory technologies. Because you will see, hopefully, during the course of this course, there's no single technology that's good at everything. You have a lot of different metrics you evaluate memories with: latency, bandwidth, capacity, scaling, energy, endurance, reliability, etc. You can keep adding. There's no single memory that's good at everything, basically. All memories have some upsides and downsides, and that's the fundamental thing that we're going to cover in this course, like how to do that trade-off analysis. So it's important to actually look at both old technologies as well as new technologies. And old technology, DRAM is an old technology. The first work at IBM was from 1965. So it's almost 60 years old, right? Flash memory is from late 70s, the first work. That's almost 50 years old. But flash memory did not become popular until early 2000s, right? With the mobile phones, etc. So even though it's an old technology, it has not been popular for a long time of its lifetime, let's say, in the history of humanity, or in the history of the time it was known to humanity, let's say. Okay. And to satisfy all the requirements, of course, right? Remember the design goals, design point that we discussed last lectures, let's say. Okay, so this is in one slide, the major trends that are affecting main memory as I see them. And I think a lot of people will agree today. Even if they didn't agree 15 years ago, I think everybody agrees with all of these right now. So clearly we have an increasing demand for memory capacity, bandwidth, quality of service, predictability, and performance in general. And clearly energy and power is a key problem in main memory, as well as the entire system. And on top of this, technology scaling of the DRAM, main memory technology that we have been using, is ending. So we're going to cover all of these quickly first and then in more detail later. So why are we having problems? Why are we increasing the demand on capacity, bandwidth, and quality of service? Because, again, computation is not a problem. We can put a lot of compute units in a single chip, or multiple chips if you wish. But a single chip, as you have seen last time, right, can accommodate hundreds of cores. If your cores are smaller, hundreds of thousands of cores if your chip is wafer scale, right? If you remember the Cerebras chip we discussed last time. Clearly, this shows that computation is not a problem today also. We are able to do this, basically. We're able to put many accelerators. Again, there are issues there, like how do we make them even more energy efficient, etc. How can we power them all up at the same time? That also happens to be a problem now. If your chip is huge, now power supply becomes a problem, right? If it's wafer scale. Clearly, there are issues over there, but I will argue that they're relatively, let's say, easier issues than we have been having with memory. And that's the technology perspective, right? Technology and architecture perspective. We can build these cores that can demand a lot from memory, and they demand capacity, bandwidth, predictability, latency, performance, everything. Applications are also demanding, right? Applications are becoming increasingly data hungry, and that's also driving all of these demands up. And also, even if applications are not demanding, or applications are demanding, we're still putting them together, meaning we have so many cores, and we can run many applications on those cores, consolidate all those applications in cloud computing, for example, in GPUs, in mobile systems. Increasingly, we want to put many applications together, run them together, and that's also increasing the demand, right? So all of these together is increasing the performance demand from memory. I think of this as performance, but it's really distinct, like capacity, bandwidth, latency, quality of service, and predictability as well. So quality of service is an aspect of performance, but it's really how much performance this particular application is getting, right, from the system. Okay, this is an example, a data point from HP Labs and University of Michigan, this paper from ISCA 2009, which may be in our reading list. Actually, maybe the scribes can actually add this to the reading list so that we can choose for the future homeworks, let's say. So what these folks have shown is that they basically analyze the trends in systems at the time. You can see that this is already 12 years old. They basically plotted the core count, showed that it's doubling every 2 years, and memory module capacity is doubling every 3 years, approximately. You can see that even though both of these are doubling, they're doubling at different rates. As a result, memory is lagging behind in terms of capacity. And they basically conclude that saying that memory capacity per core is expected to drop by 30% every 2 years. Clearly, this is not good, right? Programmers and software writers have been used to getting more and more memory to improve application performance. Well, to get used to easy application performance, let's say, waste memory potentially, and also add more features, right? That's how you add more features to your software. And if this is not going to happen, then we're going to have trouble keeping up with the software, certainly. And there are also other issues that they discussed, but I'm not going to talk about them. But this is one example of the capacity gap. And trends are actually much worse for memory bandwidth per core. Maybe we should have an assignment plotting the same thing for memory bandwidth over the years. That could be actually very instructive for you to do that research. Although it's a bit tedious, you have to go through every single year and figure out what was the memory bandwidth, what was the, and what, I guess some of this is done for you, like the core count. You can take that as a given. You just need to figure out memory bandwidth. And you will see that memory bandwidth is not increasing as fast. And I'm going to show you in a different way. Okay, let's take a look at the trends from the DRAM chip perspective. So if you look at the common DRAM chip of like 18 years, I think we have an updated version of this, but I didn't get a chance to incorporate it, unfortunately. The data needs to be a little bit cleaned. But we're looking at the trends from 1999 to 2017 over here. And we're looking at how much capacity of a DRAM chip has increased in terms of bits, how much bandwidth has increased, and how much latency has reduced. And if you plot this, I will give you the capacity. Maybe I'll ask you, how much do you think capacity has improved over the course of 18 years? Any guesses? 2x, 10x, 1000x? Somebody says 50. Okay, who else? 100? Okay, okay. I will give you the number. Basically, it's about 128x. And things have been slowing down. The scale of this is a bit weird, so ignore that. But things have been slowing down, basically. But 128x is actually not bad, right? And this is really technology scaling. Technology scaling enables us to improve capacity easily because you can reduce the size of a cell and pack more cells in a given area. We will see that it's scaling down also in real chips if you actually plot from 2017 to 2021, let's say. What about bandwidth? So here, technology scaling is on your side, basically. It's helping you. With bandwidth, you need to do something to improve. You need to improve the frequency, for example, of the bus, right? And you need to do architectural improvements to keep up. But it's a bit harder from that perspective. And I'll give you the number. It improved about 20x. And this is DDR technology. So I'm not considering 3D stacking, which we will talk about later on, where you can stack logic layer underneath memory layers and have many, many connections. This is just double data rate technology. That's, let's say, standard technology for all of these years. So clearly bandwidth has improved, but not as much. Of course, you can improve bandwidth more by, we will discuss later on also, by putting more money into it. Meaning making bigger chips, adding more pins, increasing the frequency to a very high amount. But although we've increased frequency a lot, so that's harder to do right now. But adding more pins certainly can help. But of course, that comes at a much higher cost because pins are costly in a chip and you cannot keep adding them to improve bandwidth. So this is still an issue. What about latency? How much did latency reduce? This is the common latency parameter of DRAM. We'll talk about DRAM latency a lot, but how much did the common latency parameter of DRAM reduce? 5 times? Okay, you're optimistic. It's good to be optimistic. But you get the point. I think it's going down basically as we go from capacity, bandwidth, latency. Because latency is also harder, right? Frequency is not on your side here, right? You're really trying to access. Frequency helps you with pipelining. It helps with latency a little bit, but not a lot because you're dominated by the internal latency as well as the interconnect latency. It's only 30%, right? Not so good. And I think it didn't change much basically from 2017 to 2021. So maybe 35%, let's say 40% if you're lucky. So this has not improved. And clearly latency is the cause of a lot of problems. So we're going to focus on latency a lot. And if you think about the memory hierarchy, it's designed for reducing latency, right? You have DRAM, okay, long latency. People are not improving it. That's the mindset, basically. Nobody's improving it, so I'm going to put many, many caches in the system. And the goal is really to improve latency in caching. Yes? Maybe you should press the button so that I can hear you better also. And everybody else too.
Is latency here measured in absolute or relative terms? Is it relative to clock cycles or is it absolute?
It's absolute. It's in terms of nanoseconds. You can think of it that way. Yeah. So it has not reduced, basically. Yeah, if it was relative to clock cycles, then yes, it would be bad, right? This is a bad plot. Because clearly clock cycle is, well, at least the transfer cycle on the bus has reduced. But internally, DRAM is not clocked. Internally, it's analog operation. In the array, let's say. Outside there's yeah, you need to sense it, of course. There are analog to digital converters. But internal clock of the DRAM is actually much lower than the external clock, let's say. Yeah, but this is nanosecond, so you can compare every single data point directly here. Yes. Okay.
How about now? Yeah.
Yeah, much better.
So I'm guessing the answer is no, but I'm wondering, so this plot goes until 2017. Were there any major changes in the last 3-4 years since then?
No. Yeah, but I will caveat with that. Certainly there have not been major changes in capacity and latency. But bandwidth, there have been some 3D stack technologies, and this doesn't take into account 3D stack, but they were also around before 2017. So to do a fair comparison, because 3D stack technologies are much higher cost also, because they stack logic and memory together. As a result, we do not take that into account. I mean, that gives you, let's say, maybe 5x more bandwidth. It's a one-time increase, let's say. Is that clear? But that's a good question to ask. So, well, this course will hopefully cover some potential major changes that you can make in all of these aspects. Well, bandwidth, maybe we're going to not talk about bandwidth, but we're going to talk a lot about latency. Well, I guess we're going to talk a lot about latency, let's say, because bandwidth and capacity, we will also discuss like what are the trade-offs in improving them. But we'll especially discuss how to take advantage of the large bandwidth that you have in 3D stack technologies. And we'll discuss capacity issues clearly. Okay. Any other questions? Yes, there's one more.
Does the latency really matter to like the capacity and the power of computation, or is it just to reduce the energy consumption or something like that?
So I think, let me try to understand. How are you asking how latency and capacity are related? Or
basically, I'm trying to understand how latency, like decreasing the latency, will improve the processor or the
okay,
memory.
I see, performance. Yeah. Well, we will see that a lot more in later lectures. You will see that reducing the latency improves performance, but it also reduces the energy consumption. Yes. So it's good for both performance and energy consumption. And there's also usually hidden and harder to evaluate aspects of it. It can reduce the complexity of your system. Because of the long latencies, as I mentioned, you need to build deep and large cache hierarchies today, and prefetchers, for example, to cover the latency, multi-threading. You can get rid of some of that complexity if your latencies are fundamentally lower to begin with. So in my opinion, it's good for almost everything that we value in system design. Ideally, you would like one cycle latency, 1 nanosecond, right? Even 1 nanosecond is small today, but today we can deal with 1 nanosecond, right? If every piece of data comes back to the processor in 1 nanosecond, that's great. But today it's taking hundreds of nanoseconds. Okay, I think I've shown you this picture before, but clearly there are applications where memory is critical for performance, and these applications are a lot important applications. And we're going to cover some of these applications more as we go forward in this lecture. And memory is a performance bottleneck, but also other applications like mobile, and we have a lot of applications that are bottlenecked by memory. Okay, did I show you the slide before? No, not in this. Yeah, not so far. Yeah, that's good. So this is a quote by. So we know that memory is a bottleneck, and we know that for a long time. This is a quote by Dick Seitz. How many of you know who Dick Seitz is? Nobody. You guys are too young, maybe. So Dick Seitz was the chief architect of alpha processors. How many of you know what alpha processors are? Okay, you probably know RISC-V. How many of you know what RISC-V is? Okay, that's good. Alpha is older than RISC-V. In the 1990s, alpha was king, let's say. Basically, these were the fastest processors of their time. It's an ISA. It's dead now, right now, because of some unfortunate decisions the company, Digital Equipment Corporation made, but we don't want to go into business right now. But basically, those were the fastest processors of their time, competing with Intel, for example. In fact, they were faster than Intel for a while. But later, Intel actually pushed very hard, and they made some right business choices also, let's say. But basically, after his team designed the fastest processor of its time in the early 1990s, as you can see from this paper, Dick Seitz wrote this paper, one-page article, and I will also assign you that one, which is titled "Is the Memory Stupid?" He's playing some playing with the words at the time. Probably you don't know the history, but at that time, Bill Clinton was running for the US president, and his platform was basically, it's the economy stupid. Economy is the only thing that matters, basically. And he's playing with that sentence saying, memory is the only thing that matters. And he says in this paper, one-page paper, that we designed this processor, fastest of its time. It's designed to finish 4 instructions per cycle. Every clock cycle, it's supposed to finish 4 instructions. We run this workload, important database workload. It's finishing 1 instruction every 4.7 cycles. Let's round it up, every 5 cycles, right? So it's basically operating at 1/20th of its peak bandwidth. Why? It's waiting for data to come back from memory most of the time. That's essentially the gist of the paper. And then he finishes the paper saying, I expect that over the coming decades, memory subsystem design will be the only important design issue for microprocessors. And you can see that's his emphasis only over there. And I agree with that clearly. Clearly, we know the importance of memory, right? Unfortunately, we need to do more about it, basically. So this is 1990s. This is 2000s. This is data from my own PhD thesis. I worked on tolerating long memory latencies using processor-centric techniques. Maybe I'll discuss them also. I'll give you some pointers if we have time in this lecture later on. But basically, we analyzed together with the Intel's product teams to understand what's happening in the processor. And we found out that more than 50% of the time, the processor is waiting for data to come back from memory. These are cache misses. Basically, the processor is not making any progress in this red portion. It's making progress in this portion over here. But some of that progress is wasted due to speculative execution. It's going to be on the wrong path in that green part, which we did also characterize, but I didn't put over here. So basically, it's the same conclusion, right? Most of the time, the processor is waiting for data. And these are actually the fastest processors of their time, right? Okay, so if you're interested, this is my PhD thesis. For my first paper, the first paper I've written. And you can read a more accessible version of it. And you can also listen to talks. I don't have time to talk about what the idea is, but I really enjoy the idea clearly. And this is a recent talk that I gave about it. It was implemented by multiple processors, including the NVIDIA Denver, and they actually show that it has good results. But it's a processor-centric technique. It's a speculation technique to actually overcome long memory latencies, but it's not enough, basically. It helps, but it's not enough because latencies are so long today. Okay, so this is the article that I mentioned from Dick Seitz that I would recommend you to take a look at. And this is, I guess, a recent interview that was held with me about the same topic, basically, and you can take a look at that if you're interested. But you've heard that so far. Okay, let's go fast forward 10 more years. This is data from Google, and I will also assign this paper. It's a beautiful paper that analyzes their warehouse scale computer. Can you see that? Or do I need to pull this down a little bit more? Okay, I cannot do more, but yeah. But basically, that's this 2015 paper, where they analyzed, again, all of their data center workloads, according to them. You can see these. And they basically found out the same thing. Most of the time, the state-of-the-art processor in their data center is waiting for memory. It's making progress very little fraction of the time, basically 10 to 20% of the time. It's retiring instructions. Retiring means you're actually finishing the instruction, right? It's not wasted on speculation. So this is very much similar to the data that I showed you earlier from my PhD thesis. So nothing has changed, basically, over the course of 25 years. We're designing better and better, faster and faster processors, but the processors are still most of the time waiting for data to come back. And they're very inefficient from the perspective of really finishing instructions. They're not finishing work most of the time. Most of the time, they're just waiting for data or wasting time on speculation, etc. Right? And I would recommend you take a look at that paper also. And we'll include it as one of the things that you can review for extra credit, probably, in your homeworks. Yes, please.
I'm not sure what front-end bound is.
Yeah, you need to read the paper for more detail, basically. So basically,
Okay.
let me tell you what that is. Basically, if you have, this is part of it, not everything, because they actually put together many different problems in the processor as front-end bound. But for example, you have a branch BTB miss, meaning, do you know what a BTB is? Branch target buffer. You're trying to predict this branch, which way it goes, but you miss in the branch target buffer. You don't know the target address of the branch. As a result, you need to wait. And that's one example of why the front end is not really supplying instructions into the back end. As a result, the processor cannot make progress or retire instructions. Another example could be, I don't know how they classify exactly this front end bound, but another example could be that like some queues in the front end are full for whatever reason, right? Okay, but you need to read the paper for the exact definition of what they attribute to front end basically versus back end. Back end is usually you're waiting for data to come back from memory. I think they may actually have some more things over there. That's why specifically they also attribute the things to caches, for example. Cache bound means you're really waiting for data. And that's around 50%, as you can see, on average over here. Okay, but that's a very good question. And you will see more of that in the paper. Okay, so I think this kind of proves my point that exists. So, okay, let me, what is my point? Basically, all of these studies are done on cutting edge processors, state-of-the-art processors of their time. Our study, Alpha study, and this Google Data Center study. I can add more studies here, but I think these are three most prominent ones that I know of. Today, we have state-of-the-art processors. This is one, Apple M1. It's actually beautiful, right? But similar results exist for this one also. You're waiting for data. But you can also see the effort that was put into this to actually add deeper and larger cache hierarchies, right? Like 12 megabyte over here, 4 megabyte over here, an unspecified amount of register file over here. And these are just L2, right? There are also L1s that are not reported in this picture, at least. So most of the chip is really dedicated to caches, let's say. And who knows how much there is, right? They don't talk about that. You can see that we have a complex system, heterogeneous system. I'm going to show you this picture for a different reason later on. And most of the system is dedicated to caching. Another example, this is again released by AMD. And you can see that most of it is cache. Another example, this IBM Power 10. A good chunk of it is cache. Well, I'm just circling L3 here, but there's also L2 somewhere here and L1. And this is another example. This is NVIDIA Ampere, one of the cores, I think. I cannot tell, but again, most of it is cache. Well, if it's not cache, caches are here, but a lot of it is register file. GPUs actually require a lot of huge register files, which is a form of memory in the end, right? Because those are vector registers. And you can see the numbers over here. Okay, basically memory system, the point is memory system is most of the platform, yet system is still bottlenecked by memory. So I think that should require some thinking. We're putting so much effort, but we're still falling behind. Okay, let's talk about the energy trends. This was performance so far. I mean, energy was also known to be an important concern. So this is data from an IEEE computer paper in 2003 by IBM Research, where they analyzed IBM's big iron servers, meaning huge servers that they supply to big institutions like banks, for example, to do a lot of number crunching plus transaction processing. And they found out that more than 40% of the entire system energy spent on the off-chip memory hierarchy. At that time, in 2003, off-chip memory hierarchy included off-chip caches, off-chip storage, off-chip DRAM, so a lot of stuff. But later, I think this is data from their Power 8 systems in HPC 2010, and this data from some GPUs. This is IBM, this is NVIDIA, I think. And they basically showed, both papers also showed that more than 40% of the entire system power is just in DRAM. So over the course of, let's say, a decade, power consumption of the memory has become more and more dominant in the system. Today, it's maybe over 50%. Again, these studies we have done, we've seen closer to this number, basically 40% power is in DRAM, closer to 50%. So this is going to be increasingly important. And DRAM is today, I mean, even if it's not doing anything, for example, this cell phone right now has DRAM, it's refreshing right? There's periodic refresh that's wasting energy. And we're going to talk about that as a DRAM scaling problem also. In fact, it is a scaling problem, which is going to relate this part to this part. Okay, but I think I've shown you this picture before, right? Have I? Okay, good. So I don't want to spend more time, but you've seen that there's a huge disparity in the memory access energy versus computation energy. And this was not the case again 70 years ago. Technology scaling brought us here. And I've also mentioned this one, which we're going to look at all of these papers in more detail, basically. More than 60% of the entire system energy spent on data movement. And these are real results on real workloads. Some of them are, of course, done in simulation, and some of them are based on modeling. But it's clear that, and also some of them are in real systems. So it's clear that there's a lot of evidence that shows that most of the time and energy we're spending on data movement. Okay, now let me talk about this third major trend, which is DRAM technology scaling is ending. When I was saying this in 2010 or so, not a lot of people believed it, let's say. But clearly, if you think about how technology scales, at some point you're going to reach an end. And I think we were very close in 2010 to have issues. And then clearly, RowHammer was a proof that showed that we are having issues, really. And I think we're going to have even more issues as we push forward the technology. So we need to do something about it, basically. So ITRS doesn't exist anymore, but it's an institution that used to do projections in terms of technology, international technology roadmap of semiconductors. I think it transformed into some other institute whose name I don't remember, unfortunately. You can find it online probably. But they've been projecting for some time also that DRAM will not scale easily below some nanometers, X nanometers. And they used to update it every year. I was tired of updating my slides, so I changed that to X so that you could actually figure out what that X is. So today in DRAM technology, I'm going to actually show you what they predicted. So they would basically say that DRAM will not easily scale below 35 nanometer technology. This is the future size of a technology. Basically, you can think of it as the size of the transistor or dimension of the transistor, right? And DRAM is different from logic, so it's calculated in different ways. But basically, as you reduce X, there are benefits, meaning you can pack more transistors and capacitors. You can get higher capacity, higher density. You can get lower cost, hopefully, and lower energy, because hopefully that the smaller the devices, the more energy efficient the devices. That doesn't always work, unfortunately. As you reduce the size of the device, you may get reliability issues, right? And retention issues, data retention issues. If the device is smaller, the capacitor is smaller and the transistor is smaller, it may become more leaky, etc., as we will discuss. Okay, just to get an idea, what do you think is the future size of current DRAM technology, state of the art? DRAM, dynamic random access memory. This is a tough question, perhaps. So in, let's say 9 years ago, in 2013 or so, ITRS was saying DRAM will not easily scale below 35 nanometers, 30 nanometers. Where are we around today? Yes, you may have an answer.
5, maybe?
5? You're very optimistic. It's good to have optimistic people here. 5 is probably the number that many DRAM circuit designers would love to get at, but they have no idea how. We're close, I think, in processors, yes, but yeah, even processors are having difficulty, yes. But again, it may not be very comparable because the technology, manufacturing technology is very different, actually. So we're on, let's say, 15, maybe 13, 14, getting there, basically. Maybe I'm a bit aggressive also. But these will come, basically. Clearly, we have scaled down what people said we will not easily scale below, right? But this came at a cost. I mean, RowHammer, for example, is a very good example. I think it's a perfect example of the cost because we've been arguing even before we found RowHammer that we are going to have issues. And we're going to talk more about that. Retention, I think, is an even bigger problem, actually. But it may be it may be harder to solve also in the long run. Okay, so clearly technology scaling is beneficial, but we're having difficulties. So let's take a look at this a little bit. Well, maybe we should have had that discussion over here, but that's okay. But basically, DRAM is one memory technology. Any memory technology needs to have a storage unit and an access unit. In DRAM, the storage unit is the capacitor. Access unit is really the access transistor, the bit line, sense amplifiers, all of the peripheral circuitry that basically enables you to access the charge in the capacitor and change the charge in the capacitor, right? So data is stored as charge in capacitor with charge-based memory. Later, we're going to see resistance-based memories, for example, resistive memories that are more scalable because charge units are actually harder to scale, as we will also discuss later. But this capacitor, the storage unit, must be large enough for reliable sensing. And the access transistor must be large enough for low leakage and high retention time. And as you reduce the size of the cell, both of these properties become much more difficult to maintain. Essentially, that's why we're having these reliability problems. And also there are noise effects from other cells around you, which RowHammer is an example of, right? So this was the number that was assigned. This was the X that was assigned by ITRS in 2009. They basically said 35 nanometers. Going below that is going to be challenging. And they expected 35 nanometers will be reached in 2013, right? Now you can actually pinpoint how old my slide is, right? I'm quoting the 2009 number from ITRS. So it has to be after 2009 and before 2013, specifically 2009. Okay. So basically, I think there's no question that DRAM capacity, cost, energy, and power are hard to scale. If you were taking this course, let's say 8 years ago, maybe you would still be more skeptical about this claim, right? Because RowHammer was not published, etc. But now I think there's a lot of evidence also for this one. Okay, so just as a foreshadowing, charge memories all have this problem. So DRAM and flash memory, two memory technologies that are really revolutionize our lives. One is for SSDs are based on flash memory. Clearly, main memory is based on DRAM. They're both charge-based. But as they scale, it becomes difficult to place and control charge. I've already said this, but flash has floating gate charge. But in three-dimensional flash, you have also other kinds of transistors, which we may talk about. They work on charge trapping principles. But hopefully, we will have a lecture on flash memory later on as well. But basically, in any charge-based technology, data retention and reliable sensing become difficult as charge storage unit size reduces. So this is very fundamental. I don't think there is anything you can do about it other than using architectural techniques to avoid it potentially, right? At some point, when you reduce the size of the device, how many electrons are going to be there? 1? Half? How are you going to sense them, right? So that's the fundamental physics, basically, in the end. Okay, so this is another data. I don't think I've shown this before, right? Has anybody seen it? I'm testing your memory also, including my memory. My memory is terrible these days, but your memory should be, as much younger people, better, I assume. But basically, this is another paper that we may add to the reading list as optional. This is a paper that we did with Facebook about 6 years ago, where we analyzed for over the course of 1.5 years, all of the memory errors that occur in their data centers. And they have a lot of data centers, a lot of servers. Actually, we analyzed all the servers, and they gave us access to it. And basically, this is what we found. This is a correlational study because this is a production data center. Everything is running. And we're trying to basically correlate how chip density is correlated with the failure rate of the server. And if you really want to understand how this metric is computed, you need to read the paper. I don't want to go over it right now because you need to normalize it somehow. If you don't normalize it, you may not get reasonable results. But basically, the takeaway is that the higher the density of the DRAM chip, this is a DRAM chip, employed in the server is, the higher the failure rate. Why? Because you get more errors. Again, this is a correlational study, but I think you can guess what the causes may be. And our intuition is that because you have quadratic increasing capacity, the cells are closer to each other, the cells are smaller, they're much more vulnerable to noise. As a result, fundamentally, these chips that are higher density are less reliable. As a result, this is affecting the system as errors that are exposed to the memory controller. And in fact, in this study, we found out that in many cases, you need to take down servers because of these errors. And we actually evaluate some mechanisms to avoid those cases where you have availability problems. But clearly, Facebook has many, many other issues today. Again, as I said early in the course, right, technology can be used for good or bad. And I think maybe sometimes some of these companies outweigh the good, and bad may become more prevalent. problem is when they don't realize, right, that bad may be prevalent, or maybe they prioritize the, let's say, pursuit of profit over the acknowledgement of the bad and avoidance of the bad, let's say. And I think we're going to see a lot more of those issues going into the future, unfortunately. That's why I think you're living in interesting times. Well, me too, unfortunately, but you're going to be growing up in more interesting times, perhaps. Okay, but this is very interesting, I think. This is one piece of evidence that shows that technology scaling is clearly affecting our systems, right? Okay, and you can read this paper if you're interested. It's a comprehensive study that looks at many other effects of these errors and how they occur, but I don't have time to cover that. So we also built infrastructures to understand such issues. These are FPGAs, essentially, to test DRAM, and there's a heating infrastructure also. This is based on our original RowHammer paper. We used it in that presentation. And this is a more newer version where we released it as open source. This is SoftMC memory controller, which Hassan is the first author of, who's sitting over there working on his presentation, probably for micro. That's my guess. But you can program this using a C++ API. Essentially, you can make easier to test DRAM. And the goal is to really understand why these errors are happening. And I'm going to show you much earlier versions of this infrastructure that were developed in 2011 to test retention errors in one of the later lectures, maybe tomorrow if we get to it. I mean, if this was a project-oriented course, we could actually have you do projects in this. We have a project and seminars course where actually people use the SoftMC infrastructure. But unfortunately, we already have a lot of projects in this course, and we don't want to add more SoftMC projects. But you can read it. And this is the infrastructure that has enabled us to really understand the RowHammer problem and show that you can predictably induce errors in most DRAM memory chips. And so I covered RowHammer last time. I'm going to go through this relatively quickly. You already know that it's a simple hardware failure mechanism that can create a widespread system security vulnerability. And a lot of people are writing papers about it, and also, like, let's say, popular articles about it, saying that this physics level, device level problem is really affecting our systems. Okay, and that's the paper. And this is a scaling problem, and that's why I wanted to talk about it. I showed you this picture before, but this problem, read disturbance, whenever you activate a row, you're disturbing adjacent rows. This wasn't a problem that affected real systems. The errors were not basically visible to the system until 2010. After 2010, you could do enough activates within a refresh interval that this became a visible problem. Right? And you can see that it became worse over time. In 2012 and 2013, all of the chips that were manufactured at the time were actually vulnerable to RowHammer. So this is a perfect example of technology, what technology scaling can cause in terms of reliability problems and also security problems, right? And you can argue with some of the data points. When we talk about RowHammer, maybe you can ask me why this is not getting errors over here. Okay, maybe you're asking it. So that's a good question. It could be because we couldn't exercise with the good enough patterns, right? So one of the interesting things about RowHammer is you need to really exercise it with good enough patterns. And maybe if you actually do hammering with a different kind of pattern. So for example, in this particular work, we didn't do double-sided hammering. Do you remember? We didn't discuss double-sided hammering, but basically you hammer one row, both of the rows around it get affected. So if you have a victim row, and if you basically squeeze the victim rows between two aggressor rows, you're basically doing double-sided hammering. And I believe actually we missed some chips and some rows that are vulnerable because we didn't do double-sided hammering in this work. But this was the first work, so it's okay. So later, I think there's more works, but that's a very good question, basically. Okay, and there are papers written about it. I mean, some of these we may assign also later on. I've talked about this one also, a more retrospective paper. But clearly, this is a problem. Let me show you some recent data. This paper does double-sided hammering, turns off the mitigations that are put by manufacturers, which we said that don't work anyway today. You can circumvent them. But basically, this paper shows when do you get the first RowHammer bit flip for a given chip? And it basically analyzes many different technologies. So you can see that these are three different manufacturers, three major manufacturers. There are only three major manufacturers in DRAM. And you can see that in many cases that are tested, this number is going down, meaning newer DRAM chips for a given DRAM manufacturer are more vulnerable to RowHammer. The number of hammers that you need to do to induce the first bit flip in a chip is reducing, as you can see over here. And this distribution is across different modules and chips. In some cases, sometimes we cannot attribute exactly what's new and what's old. So that's why you have some anomalies, but they're not very bad anomalies. Let's say in most cases, this number is really going down, as you can see. Okay. Okay, and these are some numbers basically. There are chips whose weakest cells actually fail only after 4,800 hammers today. Yes, please.
Why can't you name the manufacturers?
Okay, that's a good question. Well, I think that's a valid question today, maybe. This is clearly a charged issue, right? And what we wanted to avoid was really to, because any study is not perfect in the end, right? Maybe we're missing some RowHammer patterns, etc. We don't necessarily want people, so people may get the wrong idea. They may actually do comparisons between these, saying, okay, manufacturer B's chips are much worse than manufacturer A's chips, so I'm not going to buy them. So if they make such comparison, I don't want to be the cause of that comparison, because my point is not that, right? As a researcher, my point here is, this is a problem industry-wide. It needs to be solved. Let's solve it. I'm not taking sides from between manufacturer A, B, C, right? And that was the main motivation, basically. We don't want people to base their decisions, let's say business decisions, on a study that we did that always could be done better, right? Does that make sense? Yeah. That's, yeah. There's always a danger. People make these decisions based on reading a paper, right? Especially if the paper is going to be, and this is a very widely read paper. This paper actually caused a lot of industry to basically say, okay, we got to solve this problem. This data is clear. I mean, they knew that data, but they didn't do a good solution, as we discussed last time. But now I think a lot of the big manufacturers, like big systems companies, Microsoft, Google, etc., they actually pushed for the solution of the problem. We will see if they can solve it, but hopefully they will take some good ideas. Okay. Okay, so there are other papers as we discussed, and the trespass paper we discussed last time. We're going to talk more about these papers and maybe some other papers. And these are some recent papers that are coming. Maybe you're going to have special lectures on these much more recent papers, actually. Okay, so basically, clearly RowHammer is still an open problem, and security by obscurity is likely not a good solution, but it's also a technology scaling problem. Okay, let me finish this portion of the lecture, and then we're going to take a break. Okay, so let me talk about some more trends. Basically, clearly DRAM scaling has already become increasingly difficult, and we have a lot of problems. But at the same time, emerging technologies are promising. So let's take a look at that landscape a little bit. I mean, 3D stacked DRAM, you could consider that in emerging technology. Still, its costs are high, manufacturing costs are high. That's why I would still consider it as emerging technology. This is logic and DRAM. Many DRAM layers stacked on top of logic layers. Or you may not have the logic layer also. You may just keep stacking DRAM layers, right? If you want to use this as a memory chip only. This gives you higher bandwidth. I'm listing the most salient properties over here. It also gives you other things like more energy efficiency internally, right? In the stacks, etc. But most promising or most salient property is higher bandwidth. Reduced latency DRAM, people are working on it. There needs to be more work on it. Clearly, it gives you lower latency. Low power DRAM, I think it's already emerged, but there needs to be some more optimizations on low power, lower power. There are also other DRAM types that we will discuss later on, like graphics DRAM, etc., which has higher bandwidth also. And then there's many different emerging memory non-volatile memory technologies: phase change memory, STT-MRAM, magnetic memory, Intel's 3DX point. Some of them are emerged, but still their costs are high, and they give you larger capacity and better scaling. Now this is good, right? Unfortunately, there is no technology that's green at everything. So you can see that 3D stacked has capacity problems, reduced latency has cost problems, low power has latency and cost problems, and non-volatile memory has multiple problems. This is not meant to be exhaustive list of positives and negatives. So it's always a trade-off. All memory technologies have some upside and some big downsides also. Some of these are big downsides. For example, non-volatile memory. When you write to memory some number of times, the cell dies, meaning you cannot use it. That's the endurance problem. This is very much similar to flash memory. You write to a cell, let's say 1,000 times or 10,000 times, depending on the technology. You cannot reuse the cell. You cannot read from it. You cannot write to it. That's an endurance problem. And clearly, that's a problem that DRAM doesn't have, at least currently. So you run into interesting problems. So basically, because of this trade-off, what's also interesting, a major trend is designing heterogeneous or hybrid memories. And again, this is an old picture. We were advocating for it for some time. Now it's happening. And I think it's good that it's happening. Basically, since you don't have a memory technology that's green at everything, why not put together multiple different technologies that are green at different things and red at different things, good and bad at different things, basically, and design the system, meaning hardware and the software, to manage the data allocation and movement such that you exercise the greens of each technology as much as possible while avoiding the reds as much as possible. That's the idea, basically. Of course, this complicates the system now, but it can enable the technology, memory system, to scale by incorporating multiple technologies. This could be DRAM, this could be phase change memory, there could be other technologies, or this could be one type of DRAM, this could be another type of DRAM, and you could basically keep putting. Now, actually, it depends on your creativity and system design capabilities, right? So how does this enable better scaling? Now you can have much bigger memories and memories that are good at different characteristics, as opposed to having a single monolithic technology that has to be very big, right? Of course, there's a lot of work in this area that we will also talk about when we talk about emerging memory technologies. Yes.
We have a question in YouTube.
Okay.
Maybe related to this.
Go ahead.
So the question is, can we say today's compute is basically bottlenecked by DRAM, since even current NVM storages depend on DRAM?
Well, maybe, yeah, currently. I mean, yeah, current non-volatile memory technologies certainly depend on DRAM from this sense, maybe. Or, I mean, if you're looking at flash memory, you need to have DRAM inside the flash memory also. When we talk about SSDs, you need to have DRAM. I think, yeah, DRAM is a big bottleneck for sure, yes. But going forward, as these other memory technologies become better, like STT-MRAM, for example, essentially has similar latency as DRAM. If you can enable it as a counterpart to DRAM over here, they may also be bottlenecks. Okay. So I think one foreshadowing I'll have over here is main memory needs intelligent controllers. Basically, if you want to manage a hybrid system like this, you need intelligent controllers. If you want to solve issues like RowHammer, I didn't mention it over there, but you need intelligent controllers that understand access patterns and avoid access patterns that cause bit flips, basically. So to solve many of these scaling issues, you really need intelligence in the memory system that we don't necessarily have in the DRAM part today. Well, at least the main memory controller part. Okay, let me talk about some papers that are written by industry. Unfortunately, industry is not writing a whole lot of papers, but this is a nice paper that was written by Samsung and Intel in the memory forum we organized in 2014, where they basically discussed the scaling challenges of DRAM. And we're going to cover all of these actually in the soon in the lectures. Refresh, write latency, variable retention time, which is an example of refresh actually. Basically, your retention time changes randomly over time, and this becomes worse with technology scaling. And they basically say that you need intelligent controllers essentially also, which is what we have been arguing even before this. But it's good. And this is actually the only paper that I know of that Samsung and Intel have written together. These companies don't normally even talk to each other, interestingly. Okay. So an orthogonal issue, which is also important, but it's really independent of scaling. It's important, well, it's caused by other kind of system scaling, not main memory scaling necessarily, is interference in memory. So we have all these cores and agents and accelerators, and they share main memory as a medium. And because they share this medium, cores interfere with each other when accessing this shared medium. And as a result, uncontrolled interference leads to many problems like quality of service. For example, when this core is accessing main memory and another core may not be able to access it because the requests clash in the same bank, right? Conflict in the same bank. And we will see that some access patterns actually deny service to other access patterns, hopefully today, but we will see. And this is becoming a bigger problem. Basically, can we somehow enable quality of service and high performance in a system that's becoming more complicated? CPUs, GPUs, hardware accelerators like the Apple M1, right? That has neural engine, GPUs, large and small cores. So all types of agents are accessing main memory. And clearly there's interference between them. They all have different demands also. You may be running, I don't know, an important inference application over here and another important CPU application over here. Which one do you prioritize? And how do you allocate resources to these heterogeneous agents to mitigate interference between them and to provide predictable performance becomes a bigger problem. And we're going to discuss this in the course of these lectures. Maybe in the next part of this lecture, I believe we'll go over that. But again, if you want to do this, you need to have some intelligence in the memory controller. The memory controller needs to understand the demands of different applications that are running in different cores, accelerators, etc. It needs to basically balance the requests that are coming from them. If something is critical, you cannot deny that a service to that. And again, I think it's a huge system design problem because it really relates to the operating system scheduling of the applications on the cores as well. Because there may be no way you can actually satisfy the demands of all of them, right? At the same time, if you didn't do a good job in terms of scheduling the workloads. Okay, so I think hopefully that shows you the point that main memory needs intelligent controllers. So I think this is a good place to take a break. Any questions? Another question? Okay, go ahead.
So yeah, we have one more question in YouTube. So did you test GDRAM on RowHammer? I guess the question is like, I think the GPU workloads can be hammered, but they are mostly error tolerant. So.
Well, yeah, we didn't do that particular study. Like, I think what you're saying is GPU DRAM, or yeah, I think fundamentally any type of DRAM that is scaled should have the RowHammer problem for sure. But we didn't do that particular study. Again, error tolerant could be possible, but that's an independent study, right? There are two studies here. One is whether the DRAM type is fundamentally vulnerable to RowHammer, and the second is what effect does that have on the application. And I think both are important questions. My feeling is like any DRAM that is scaled to smaller size technology nodes is vulnerable to RowHammer. I don't see any reason why GPU will not be. But of course, how RowHammer affects the applications that are particularly running on a GPU is another study potentially. But again, my feeling is that there will be some applications that are affected significantly. Because even though you may actually have some tolerance, you can easily do RowHammer so that you can induce a lot of bit flips. And I don't think applications naturally have that level of error tolerance to get rid of it, especially if someone's maliciously attacking you, right? They can actually overcome any tolerance you may have because the tolerance is really not infinite, let's say. Yeah, from an attack perspective, I think it's going to be hard to, let's say, tolerate RowHammer by saying, okay, these applications are tolerant. From a reliability perspective, then you're thinking, okay, what's the probability of RowHammer happening without somebody attacking you? And that's very low. Okay. Okay, we'll talk more about RowHammer in one of the future lectures and go into more detail. Okay, if there are no questions, I think we should take a 16-minute break. 2:35. Yeah, I'll see you soon. Maybe I should do the lecture break here. Okay. This is. Say it again. Oh, okay. Yeah, that's a good idea. You're right. Oh, yeah, I need to put this on. Okay. Is it significantly better? Can I put it on? Okay, for you guys also? Okay. Is it good now? Okay, excellent. Okay, so this is still lecture 3A. Basically, I wanted to cover challenges and opportunities and also solution directions. We kind of talked about some of the solution directions, but I want to give you a broad perspective and also kind of my personal journey a little bit. And then we're going to focus on go deeper, basically. So basically, I think hopefully it's clear that we somehow need to solve the memory problem. And again, this is true in research as well as development. If you go to industry, for example, start a job, if you're doing software or hardware, you will see that memory is a big bottleneck and you will need to overcome it somehow and solve it. Maybe within your limited domain of the job, depending on the job you have. And if you're a system builder, you want to design much more efficient systems, you will see that this is an even bigger bottleneck in your face, let's say. So you need to solve it somehow. As a researcher, of course, we want to be longer term, right? We want to solve it for good, let's say, or get it to a point that it's not the bottleneck, let's say. So how do we solve it, basically? So I think I have 3 directions, and we're going to cover all of these directions in this course. First of all, I think we somehow need to fix it, meaning maybe you don't change the technology drastically, but make memory and the controllers more intelligent, like what we've been arguing for, right? So far, there's little intelligence in the memory controllers as well as memory. Why not make it better? Why not re-examine the interface we have to memory, re-examine the functions we place on memory, re-examine the architecture that it has, and co-design it together with the system so that it doesn't appear as a bottleneck to applications and the system and the users. That's the idea over here. I call this system memory co-design. You may see this word in other places also. And I think this is definitely a good direction. This is independent of the technology in a sense, right? It doesn't matter whether you have SRAM, DRAM, flash memory, new memory technologies, doesn't matter. You still want this sort of change to enable that things don't become a problem. The second direction, as I said, orthogonal, is maybe some technology is there to eliminate or minimize the problem, right? It doesn't look likely that this will happen, but it's good to still invest in this direction, or at least solve some of the problems that are associated with existing technologies. Basically, if you can replace with DRAM with a different technology that's fundamentally better in many aspects, maybe that's good. Again, I said, as you will see also, that this is not looking likely at this point. More likely, you'll need to augment DRAM. Maybe you have not as much DRAM that you need. Maybe you have a small amount of DRAM and a large amount of phase change memory, for example, that's more scalable in the system. So that's a potential solution. But of course, once you start doing that, maybe fixing, you're also coming into the territory of the first part, right? How do you actually partition the duties between DRAM and phase change memory, for example? So I think all of these different directions need to be examined together at some point. But the second direction, if you take it independently, it's really about thinking about new technologies, enabling them, architecting them, and which will hopefully enable system-wide rethinking of memory and storage. As we discussed, maybe memory and storage should be combined in future technologies, right? Or partly. And the third direction I think is also important, is somehow embracing the problem, basically. Okay, we have all these problems with memories. None of the memory types are perfect, and we can build different types of memories that are good at different metrics. Let's do that. Let's have a lot of heterogeneity in memory and map data intelligently across these different memory types so that we can take advantage of the good characteristics of different memories while avoiding the bad characteristics as much as possible, right? From the reliability perspective, for example, you can map the error tolerant data to memories that have more errors. And if you can keep the errors under control, then this may actually work well, right? And I think this can lead to new models for data management and maybe even usage, which we have not fully considered. I think people are looking into it right now, but I think there's certainly more to do in this area. I think these are distinct directions for sure, the way I pose them, but I think you can employ all of them together also and combinations of them. But I think regardless of, maybe there are some other directions also. If people have ideas, please feel free to talk about it, or maybe in later lectures, we're going to cover some examples of these. I think in the end, solutions require some hardware, software, device cooperation, basically. In all of these directions, actually, you need cooperation between different components, between software and hardware. I don't think there's any other way. That's why we talked about the hardware, software, co-design, system level design at the beginning of this lecture, right? Cutting across the hierarchy, basically. Now let's talk about this. I'm going to briefly talk about these three directions. So this new memory architectures, because we're going to focus a lot on the new memory architectures. How do we overcome the shortcomings of memory? I think this, I call also this memory-centric system design. Basically, design the system such that it's more memory-centric, such that you can eliminate memory as a bottleneck. I think this leads to new memory architectures that we haven't considered, interfaces and functions, and also better waste management, potentially. So if you're wasting memory, if memory is such an important resource, and if we're wasting it, maybe we should not waste it, right? And we will see examples of this. For example, in modern memories, a lot of the data that you have is zeros. There have been a lot of studies that show that you have, I don't know, 16 gigabytes of DRAM, 30% of it is zeros, if you look at the content. That's a lot of waste, right? So why do we need to do that? So if you have good compression mechanisms, maybe you can eliminate some of that waste. Basically, everything helps. Again, there have been a lot of studies that show that you're bringing large cache blocks into the cache. So you're transferring, let's say, 64 bytes or 128 bytes, and you're using only 1 byte out of it. So you're wasting a lot of the bandwidth. Internally, inside the memory, we'll cover the inside internals of memory architecture. You will see that you're actually transferring even bigger blocks, like 8 kilobytes. So 8 kilobytes, you fetch 8 kilobytes at a time, which is a row. Only 1 byte is being used. So does it make sense, basically? There's a lot of inefficiency in the fetch. A lot of that fetch is wasted. So these are some examples of waste over here. Similarly, latency is wasted. So we'll also talk about these works, but a lot of works also show that the memory controller is waiting for memory to give the data, but it's waiting too long. Meaning there's only one set of latency parameter that says, okay, wait for, there's a contract between the memory controller and memory saying that wait for 15 nanoseconds. I'm just making it up. But under common case conditions, low temperature, for example, and I guess average memory module, you can only wait 30 nanoseconds and the data will be fetched reliably. So there's some margin in the memory timing parameters that are put in. So it's really wasting the latency. Why is it there? Because of the way we think about memory latency. You basically have a single latency in mind, and that single latency needs to be correct regardless of the operating conditions. If I'm operating memory at 95 degrees Celsius, it should still work. If I'm operating it at the lower end of the temperature specification, it should still work. But in the common case, maybe 50 degrees Celsius, right? The latency, you don't need to wait for that long because cells are much more reliable at 50 degrees Celsius compared to very hot temperatures and maybe very cold temperatures also, right? So I think these are the kind of issues that lead to waste because you're specifying something for all modes of operation as opposed to common mode of operation or the operating point that you're at. So we're going to see a lot of these examples of waste. So I think removing waste is actually always a good idea first. And I think I will show you a lot of studies that prove that there's a lot of waste in memory. That's good, but I think that's not enough again. Okay, so there are many key issues to tackle, and we're going to cover a lot of these. Enabling reliability at low cost, leading to hopefully high capacity, enabling better scaling going into the future. That's important, and that's why we're going to focus on that a lot. Reducing energy is important. And these are two sides of the same coin, actually. If you want to enable reliability, you can do it by increasing the energy, right? For example, with RowHammer, you can increase the refresh rate a lot, but that causes energy problems, right? So ideally, you would like to enable reliability with low energy, but that's the difficult part in the research. Reducing latency, as we discussed, improving bandwidth, reducing waste, as I discussed a lot on the slide. I think these are all important, actually. And enabling computation close to data can improve all of these at the same time. That's why we're going to think about changing the paradigm, meaning doing computation next to the data or wherever the data resides as well, so that we can actually get rid of a lot of these at the same time. Well, maybe that doesn't fundamentally get rid of waste, but you need to do something else on top of it. So, okay, so this is one example. And I think there are a lot of works that we're going to look at These are some of the works for my group. Now they're increasing, as you can see. That's why the font size, I had to reduce it to 4 or 3.5 or something like that. We've been working in this area for more than 10 years now, actually. There are a lot of exciting ideas, I should say. And I don't think I've included the latest works over here. And maybe I missed some of the works also. Okay. The second solution direction, which I also mentioned, is emerging memory technologies, right? There are some emerging technologies in general. They don't have to be resistive, but I put resistive over here because those are the most interesting ones today that we know of. These are more scalable than DRAM. And they're also non-volatile on top of this. So this is very interesting because they have characteristics that DRAM doesn't have, and also they're better at scaling. One example is phase change memory. Again, this is very old technology. It's used in rewritable CDs, for example. But more recently, people have found out, or people have developed mechanisms to actually read it reliably and fast without using light. Basically, you don't need optical reading right now. And I'm not going to go into the details of it right now, but I'm going to refer you to some paper if you're interested in doing that. We'll have a lecture on emerging memory technology, specifically focusing on phase change memory. But data is stored by changing phase of material. Material could be different things like chalcogenide glass. And data is read by detecting material's resistance. The material may have some high resistance state, low resistance state, and many different levels of resistance in between, depending on how you change the phase of the material. So basically, you store data in terms of the resistance level of the material. And this can enable actually different levels of storage, meaning with a single cell, you can store maybe 4 bits, let's say, right? Because you may have 16 different levels of resistance. It's similar to flash memory, as we will also discuss, multi-level cell technology. But the key thing is you detect materials resistance, and resistance is what determines the data storage or the value you store in it. And these are old numbers again. From 2009, it was expected to scale to 9 nanometers. In 2022, it was supposed to reach 9 nanometers in 2022, basically. I don't know if it's there at this point, but current projections say that it can scale down to even smaller nanometers easily. And Intel's 3DX point is one example. I'm not sure if they have publicly admitted that it's phase change memory, but it's clear that it's phase change memory based on the record of publications. But basically, it's much more scalable. And this is a beautiful paper that was written by IBM Journal of Research and Development, IBM folks who were working on the phase change memory technology, that show that you can they basically prototyped phase change memory at 20 nanometers. This is 2008, as you can see. DRAM reached 20 nanometers. Again, comparatively, if you do a ballpark comparison, maybe around 2016 or so, right? 2017 or so, maybe 18. I don't know. Don't quote me on it. Okay, and it's also expected to be denser than DRAM. So it's expected to be denser than DRAM because cells are smaller, but you can also store multiple bits per cell. You can divide the resistance range into multiple levels, as I said. It's very hard to do in DRAM. You need to change the sense amplifier significantly to sense charge in DRAM. And as charge level becomes smaller, it becomes harder and harder to actually sense multiple levels of charge. Even sensing 2 levels, meaning 0 and 1, is difficult, right, today. And it's going to be more difficult going into the future. Okay, of course, these are good things. Emerging memory technologies have many shortcomings as well, depending on the technology. Latency is a problem, energy is a problem in phase change memory, for example. How do you do writes are a problem, endurance is a problem. The key question is, can we somehow enable them to replace, augment, or surpass DRAM? And in some cases, they can surpass, right, if they're used as non-volatile memory, persistent memory, for example. So we're going to try to answer this question also. And there's a lot of work in this area. This is my group's work. It's not as much as the DRAM work, because DRAM, I think, is a more mature technology. So it's easier to do experiments on DRAM. It's harder to do experiments on a technology that's not mature, that you do not have access to. But we're going to cover some of these works and some of the other works in the field as well. Okay, and as I mentioned, it makes sense to have a combination of hybrid memory technologies. And we're going to talk about that as well when we talk about emerging memory technologies going into the future. But keep this in mind, keep this picture in mind whenever we're talking about other topics in memory as well, because this is really the future that's happening in a sense. Okay, I think I've discussed this before, exploiting memory error tolerance, right? We did this in an earlier lecture. Do you remember? Okay, good. So basically, This is one example of emerging memory technology, not emerging, a hybrid memory technology, and you can take advantage of and construct by exploiting some application properties, right? It doesn't have to be phase change memory. It can be, but it could be different types of DRAM. And based on the vulnerability of your data, you design your memory such that you can have a lot of it can be low-cost memory, and hopefully a small fraction has to be very reliable. And you put them together, and it's called heterogeneous reliability memory. And there's a huge design space that maybe we will discuss when we cover heterogeneous memories more. But since I covered this already, I'm not going to talk about this more at this point. But this is, again, an across-the-stack solution, basically. Somebody needs to provide the memory error tolerance, which is not a easy thing to do, right? How do you characterize what's your tolerance to memory errors? Programmer may have an idea, but they need to somehow quantify it, right? And then communicate this to the hardware and the software, and then design memories that can actually cater to different needs of the applications. So this sort of thing can be done a lot more easily if your system is special purpose. If you have one application you're optimizing for example, deep neural networks. This is actually a perfect fit for deep neural networks, let's say, because you know your data characteristics much better. You're not designing for all of the applications in the world, right? You have no idea about all of the applications in the world, but you know which neural networks you're designing for. You can characterize them. You can even train them based on the error characteristics of different memories, such that you don't get accuracy problems. And then you can basically have this sort of memory in your machine learning accelerator that can be much more efficient and much more scalable, right? That's the idea over here. So sometimes the ideas may not be easy to implement in the general purpose domain, because this is really hard to do for all applications, as you can imagine, right? But in the special purpose domain, it can be relatively easier to implement. And we're going to hopefully see an example of it. But we did this work in some applications, and you can see that the heterogeneous reliability memory has actually provides you, let's say, a good point in space. You can see that you're almost always you're optimizing for multiple metrics. There's no single metric. You can see here, we don't have performance here because we assume the performance will be the same minus the availability part, for example. But you can see that the cost savings, because you reduce the error correcting codes, and then there's memory cost savings, and there's how many queries you get incorrect, how much unavailability you have, and how many crashes do you have. So using heterogeneous reliability memory, you can actually get a good point in all of these compared to all of these other comparison points. So if you make memory completely unreliable, let's say less tested is an example of it, it doesn't look good, basically. You need a combination of reliable and unreliable memories. If you make memory completely reliable, which is the typical server, you can see that it's not as good in some metrics over here, which is the cost especially. Right? Okay. I mean, you can read the paper for more detail. I don't want to explain that figure completely, but basically, as you go inside, it's bad. As you go outside, it's better over here. Okay, and that's the paper. And I think this heterogeneous, I don't know why this didn't go away. Okay. Heterogeneous reliability memory is an example of the axiom that we discussed multiple times in this course, basically, expanded view of computer architecture, right? That's one example. You specialize the memory for the characteristics of the application as much as possible. Okay, you can think of this as actually for other metrics also, right? Memories with different latency characteristics. Not all applications, not all parts of an application need low latency. Not all parts of an application need low bandwidth, high bandwidth. But of course, now the design space is huge, right? How many different types of memory are you going to design? And that becomes the art part of computer architecture. Okay, the orthogonal issue of memory interference, I think this is important. And hopefully, if we have time, I'm going to focus on the memory interference part. Okay, hopefully we will have time. I want to cover the course logistics also, which we didn't cover. But let me finish a high-level overview of the memory interference first. But as we discussed, the memory interference between cores is uncontrolled, mostly. There have been a lot of efforts in this. It's become much better compared to the past, but we still can do much better. And this leads to unfairness, starvation, and low performance. I'm going to give you examples of this later. And this leads to an uncontrollable, unpredictable, and vulnerable system. Basically, some application can deny service to some other application because of its access patterns to memory. And this should not happen. And the solution is really designing more predictable or quality of service aware memory systems. How do we make the memory system service different applications more fairly based on the quality of service requirements of the application? So I will discuss this later on more, but hardware is designed to provide a configurable fairness substrate. So if your hardware is completely unfair, you cannot control it, right? And we will see examples of this later on. You will see what I mean soon, hopefully. But if you provide a fair hardware substrate, the software can configure the substrate so that you can satisfy different quality of service goals. If an application requires a lot of memory bandwidth per, let's say, second, you can hopefully configure your memory controller to enable that. If an application requires some latency guarantees, you can hopefully configure your memory controller such that it can obtain that latency guarantee if it's obtainable, right? It may not be obtainable also, right? Based on the other applications that are running in the system and sharing the memory controller. So this is going to be more important than quality of service aware memory systems can provide predictable performance and higher efficiency. I'm going to talk about some approaches, but this is one approach to the problem, basically. If you want to satisfy performance requirements of different applications, SLA is also service level agreement requirements, which is essentially performance contract, let's say. In the presence of shared resources, how do you do that? One approach is to have techniques or models that can accurately estimate how good is an application doing in the presence of other applications that are sharing the resource with it. Like, what is my performance loss compared to what I should be achieving? If you can have a good model of that, which is not easy actually, as we will see later on, then you can use this model to drive decisions, basically. Drive mechanisms in hardware that can enable resource partitioning or prioritization that is needed to achieve the required performance levels for applications. For example, if you know exactly how well each application is doing compared to the requirements, individual requirements that they have, you can push this information to the hardware, or how the hardware can collect that information depending on what kind of interface you have. And the hardware and the memory controller and the caches, for example, change the partitioning, change the prioritization such that applications that are not satisfying their requirements are prioritized, right? You can give more space in the cache to an application that's not, that's slowed basically, that's much slower compared to what it's supposed to be achieving, right? You can prioritize in the memory controller as opposed to prioritizing some other applications' memory requests. And I think this is a good direction for sure. Of course, you need to do this all the while providing high system performance, because if you don't want to provide high system performance, this problem is really easy, right? Run just one application in isolation, it will finish. And have many, many servers where each server is a 100-core machine, but it's running only one application in one core, let's say. But that's terrible in terms of efficiency, right? You're not really providing high performance that way. So you can provide performance isolation, but the question is at what cost? Okay, and these are some of the papers that we may cover if we get to it. But if you're interested, I would recommend looking into it, because these are some works that have showed that you can actually provide predictable performance in the general case with general purpose applications. And you can estimate their slowdowns and also partition the resources between shared caches and main memory across different applications in shared cache and main memory, so that you can actually provide, you can control the interference between applications and provide achieve the performance guarantees or performance goals each application requires if it is achievable, right? In most cases, because there might be some cases it may not be achievable, right? Somebody scheduled so many applications or so many badly interfering applications at the same time on the multi-core system, all of them are slowing down. And there's nothing you can do in the hardware by partitioning the caches or partitioning the memory bandwidth, memory controller prioritization to achieve the goals of all applications, right? This is a hard problem. So you really need system support at some point. The hardware may say, okay, with the current applications you've provided to me, I cannot achieve the goals that they want. So take some of the applications away. So this is a system level problem also, as you can see. Okay, so let me tell you quickly about we've been talking about the intelligent memory controllers, right? I think this is fascinating because I had no idea I would be working on memory controllers. But in fact, this is one of the first things that I did when I started my PhD. I'll give you my personal journey a little bit as well. So, okay, before that, I guess, memory control is getting much more complex, as we discussed earlier. There are many goals, many constraints, many metrics, and many agents. and a lot of complexity over here. If this becomes DRAM and hybrid memories, how do you actually guarantee that in the presence of heterogeneity in the agents as well as heterogeneity in memories? So I think this is actually a very fascinating problem. And we need all kinds of approaches to it. We need practical engineering approaches. We also need, I think, more theoretical modeling type of approaches to really understand how we can partition the resources over here. And I think we also need machine learning based approaches, which I will maybe mention over here. But just to give you an example, I mean, this picture was my cartoonish picture, right? From I don't know when, but clearly systems are really like this today, right? In fact, there's a lot of similarity over here. CPUs, GPUs, hardware accelerators. This thing has, where are the CPUs? Different types of CPUs, GPUs, hardware accelerators. Some of the caches are shared between some components, and clearly the memory is shared by all of the components. So this picture is real, let's say. Maybe it doesn't have hybrid memories, but I can guarantee you that that's going to happen down the road. Okay, so it's a similar picture. So just want to tell you my personal story. This is actually the first patent that I've written. I did an internship at Intel with the Nehalem group at the time. And we wrote this patent, and Intel decided to name it so generally like this: method and apparatus to control memory accesses. It's about memory controllers that prioritize between prefetches and demands, basically. I like the idea still, but that's how we started doing memory controller research. And it's fascinating that we still need to do memory controller research. I didn't do my PhD thesis on this topic. It was a totally different topic, but I like this topic also quite a bit, as you can see. So we're going to cover this paper at the end of this lecture today, hopefully, after we cover the course logistics, since we didn't get a chance to cover them. But I want to spend a little time on course logistics just to answer your questions, maybe. But just to give you the story, we have also done a lot of other work on memory controllers. Later in some lecture, maybe after lecture 12 or so, we're going to talk about this memory interference problem even more. So there are a lot of solutions, basically. And I like some of, clearly I've done, I've been part of these works, and clearly I like many of them. But actually, these have had a significant impact. Like this PAR-BS mechanism partially was implemented in Samsung memory controllers. And we received nice reviews related to this. For example, this was a review from ISCA conference. I may show you later reviews from not so nice reviews, let's say, from some other conferences. But this is kind of nice, right? When it was accepted. Later, we did a lot of other work on quality of service aware memory controllers, and maybe we'll get a chance to talk about Bliss. It's a nice name. It's always good to name your mechanisms nicely, I guess. Bliss is a very practical approach to memory control, let's say. It doesn't cover everything, but it's quite useful in my opinion. And then heterogeneous system scheduling. And then this may be the state of the art in this topic at this point. I mean, there may be minor improvements on it, but basically this looks at the whole problem. If you have CPUs, GPUs, hardware accelerators, how do you actually do the scheduling? And that's a complex scheduling problem. Well, this may be the state of the art without machine learning taken into account, I should probably say. So we're going to talk about that also in a little bit. This is a different direction, like predictable performance. That's also important. That needs to be looked at. But basically, memory controllers are really critical to research, and they will become even more important. I think I said this 20 years ago. I will say this right now, and I may be saying it in 20 years later, but hopefully we will have much better memory controllers down the road at that time. I believe we have much better memory controllers today compared to 20 years ago. By the way, that patent was from 20 years ago. We filed it in 2001. Maybe we filed in 2000. I don't remember now. Okay. Yeah, basically memory control is getting more complex. So we really need to look at other approaches also. And this is an example that we looked at in 2008. Well, it was published in 2008, but we started looking at it in 2006. And the idea is to use machine learning approaches to actually do better scheduling, request scheduling. And it turns out these are actually quite good approaches. And it's not a neural network approach because that's expensive and that may not be a good fit. Whenever you want to apply a machine learning to a problem, you will need to understand what kind of machine learning approach should you apply, right? Because you have a specific problem, memory scheduling in this case, which requests should be prioritized over others with a goal. What fits, right? And in this case, because that problem is very dynamic, it requires a lot of interaction with the workload and environment, and you don't know whether you've done the right thing anytime soon. Sometimes you do, maybe, potentially, but usually whenever you schedule one request over the other, you don't get any feedback as to whether you've done something right or wrong, right? The feedback is in the form of whether you improved performance, but that's not direct feedback unless you measure it. And even if you measure it, when do you measure it? That's the question, right? So if you don't have immediate feedback as to what you've done is wrong or right, that guides you as to what kind of machine learning approach you may want to apply, right? So for example, if you want to train a neural network, usually you want some feedback as to whether what you've done is wrong or right. For example, image recognition is what neural networks are quite good at. And you really want clear feedback as to whether this image is a cat or a dog, right? But here, you have no idea. That's why we chose the reinforcement learning approach. Basically, you get delayed feedback at some point about your decision, and that delayed feedback reinforces the action you take in a given state. And essentially, the memory controller is an agent, like a human. You take an action. At some point, you get some feedback as to whether that action was right or wrong. Again, there's no right or wrong. It as an indication of whether the performance improved or not improved, with some potential heuristic, of course. And then based on that, you reinforce the action you took in a given state, right? That's the idea over here. So as humans, we're also reinforcement learning agents, basically. Some people in psychology claim that we're only reinforcement learning agents, actually. That's the only way we learn. I don't believe that, actually. I think there are multiple ways we learn. But reinforcement learning is actually a good way of learning, basically. You take an action. At some point, you get a reward or punishment. Punishment is a negative reward, essentially. And based on your interpretation of whether that action was taken in what state, you basically associate the state with an action that maximizes your long-term reward, hopefully. That's the idea. And the next time you see a similar state, you basically take the action that maximizes your reward. That's the idea of reinforcement learning. And I think that's a great fit for memory controllers, for example, as we have shown in this work, as others have also improved on later on. And maybe other types of system problems that essentially require, that essentially have similar properties. So we have a paper coming up at Micro, for example, that applies reinforcement learning to prefetching, data prefetching. There, again, you have a similar problem. You prefetch some data. You have no idea whether you did the right thing for a while. Or maybe you never find out, right? Because you may prefetch some data and hundreds of, maybe tens of thousands of cycles later, the processor actually uses it. The processor may never use it, right? So the feedback is very much delayed. And it's not just about processor using it. It's also about the other stuff that you're causing. You may actually cause pollution in the cache. You may actually waste bandwidth. Well, you always need bandwidth to prefetch. So you have all these interactions with the system that a single metric, correct or not, doesn't take into account, right? So an unsupervised learning approach like reinforcement learning can be very useful in those cases where you're interacting with the environment dynamically, and there are multiple things that affect whether your decision is good or bad. Okay, so I spent some time over here because I believe this is actually an important part of the future of system design. How do we actually design more intelligent controllers in our system, whether it be memory controllers, cache controllers, schedulers, whatever you think of? Can we make them fundamentally more intelligent? And instead of having them be designed by humans dictating the policies, can they actually learn over time based on their actions, right? And hopefully learn to do the best thing for a definition of best, of course, right? And that's the idea. So I think there's a huge future over here in the design of systems. So some people call it, I think this is for machine learning for systems, let's say. How do we use machine learning for designing better systems? I call designing more intelligent systems second, self-optimizing systems, as we said over here. And I think this is a good time to actually work on that topic. Okay, so clearly there are many new problems and many new directions, but I think this is another example of intelligence in the memory controller, frankly. We need more intelligent agents as opposed to other capabilities in the memory controller. Okay, so we will see more examples of this. I think machine learning in computer architecture is also an example of this expanded view. Even though you may actually be stuck in one area, usually you need to span multiple areas over here. Okay, I think that I'll talk about this in this interview also, as I mentioned last time. Okay, so what will we cover in the next several lectures? Any questions so far? Okay, yes, please. Can you press the button? Yeah.
So the reinforcement approach is good because I guess it allows you to have less what's it called, a priori knowledge about the specific application, and yet also has the trade-off of requiring more resources. So would you say that the main target area for this one would be like general purpose applications where it should optimize to where there is like low variance in the use case, and maybe it would be less optimized for like I guess like more tunneled visioned applications?
Yeah, so that's a good point. I think I would agree at a high level, yes, because if you're limiting your application space, and if you know your memory access patterns extremely well, for example, you can customize your memory controller for that, right? If you know that, do it. You don't need machine learning for that purpose, probably, right? If you have enough knowledge about your access patterns. This is very useful, in my opinion, when you don't have enough knowledge about your access patterns, right? You have no idea what's coming, well, or maybe you don't have good enough idea, so you learn based on the past decisions. So I think fundamentally, I agree, yes. But if you may still have an application that's specialized where your access patterns are very much data dependent, user dependent. In that case, I think this could still be useful, even though your system may not be general purpose. Make sense?
I think so. It was just, I was thinking like one of the trends you mentioned as to these days why we need to improve the memory is because things are getting more intensive, like data intensive and stuff like that. I was wondering, like in those kinds of situations, is there actually, and like, is there a correlation between something being more performance dependent and also it having less variability in the usage of memory?
I see. That's a good question. I mean, it could be, right? You may have very high bandwidth requirements, but that bandwidth requirement may be very regular, meaning you may be streaming out of memory, and that's all you do. In that case, the access pattern is simple, let's say. You just have a very high bandwidth requirement in that access pattern. So it's certainly possible. In my experience, applications come in all varieties. Sometimes you may be very intensive, but you may know exactly your access pattern. Make sense? Yeah. Okay. Any other questions? That's a very good question. I think that touches the issue of the special purpose versus general purpose, and when you can really customize a system component to an application. I think when you know your access patterns, go and customize it. Okay. Okay. Okay, so just an overview of what we will cover. I mean, we'll cover course logistics, and hopefully I will be able to cover memory performance attacks today also. But tomorrow, hopefully, we will start with data retention. Well, memory interferences today, hopefully. We'll see. And then we'll cover RowHammer, more detail, hopefully. And then we will go into new execution paradigms like computation and memory processing in or near memory. Hopefully, that'll be exciting. I mean, in all of these, we can cover actually, we can almost dedicate an entire, well, in computation and memory, I think we can dedicate an entire course for it, but we're not going to be able to do that since we have a lot of other things to cover. We're going to talk about low latency memory. We're going to touch on data-driven architectures and data-aware architectures. Data-driven, so the self-optimizing memory controller is one example of data-driven architectures, meaning architecture makes decisions based on data. It's driven by data, as opposed to a hard-coded algorithm designed by a human. I think of this human-driven versus data-driven. Data-driven means you basically optimize yourself based on data. And we're going to talk more about memory controllers and understand the basics, and also talk about quality of service. And in all of this, we'll cover guiding principles and research topics and trade-offs. Does that sound like a good plan? Okay, this is just next several lectures. We will have more after that. Just some recommendation of papers. As I mentioned, this is an early paper that we delivered at a conference, and I would recommend looking into it because it's always good to look into those papers that are, I guess it's not old, but relatively old in terms of the amount of things that have happened in the last 8 years. And I think it's good to look at it. I think this may be one of the papers. Actually, this is the paper that I assigned. This is a longer version that talks about memory scaling issues. That covers a lot of the issues that we're going to touch on. And some of these papers are already in your homework that I would recommend to take a look. And in fact, you can review the papers and you can get extra credit for them also. So I think this may be my last slide. Basically, these are the challenges in memory scaling. We're going to cover all of these, but I think it's good to keep this in mind again. It's just like a summary slide. Data retention, we're going to talk a lot about. Reliability and vulnerabilities, RowHammer could be one of them. Well, it is one of them, but there may be others. Latency and parallelism and bandwidth issues. And we'll talk about bank conflicts, for example. It's a big problem. Energy and power. And I think memory's inability to do anything more than just store data is a big chunk of the problem also. So if you actually add more intelligence to the memory system, we aid memory scaling as well. Hopefully this will become more clear when we get to it. Okay. Any more questions? Otherwise, I'm going to switch to the next slide. Yeah. Okay, I stopped sharing. This didn't disappear. Yeah. I thought that would also disappear, but it didn't disappear. Okay. Should we cover course info and logistics? What do you think? Or is it boring? Okay, I guess some people don't find it boring, so we'll cover it. I don't want to spend a lot of time on this. Yeah, I need to reshare. Yes, you're right. So which one? This is so small. Okay, you can see it now, right? It's another thing that we need to fix. Default should not start here. Okay. Okay, what did we do last time? Okay, good. Okay, let me quickly cover course info and logistics and take any questions you may have. I think a lot of this was answered at some point, but maybe you have some other questions. I'll go over this quickly. Clearly, I've introduced myself. If you're interested in more, you can find out more. I think I've introduced the teaching team also, right? Atwan is in the back. Mohammed is also over there. Who else do I see? Hassan is here. John is here. Joao is here. Anybody else? Am I missing someone else? Okay, I think that's it among the big team. So this is a big team clearly, but some people will be more specialized for different labs, and we will tell you who to go to for different labs, right, Mohammed? So we'll give you more information as to who to approach for a given lab or homework, for example, since not everybody is involved in the preparation of everything. So keep that in mind when you approach TAs. You don't want to go to a TA who has no idea about a lab, for example. Usually they have some idea, but if you go to the specialist in that lab, you will get better help, let's say. Okay. Yeah, I would suggest getting to know them and their research as well, because they're all doing research in the group. Okay, I'll go through this relatively quickly. Hopefully, we will talk about how a computing platform works with a focus on important issues, let's say. We'll prioritize the most important ones. Hopefully, this course will give you an idea of how decisions that are made in hardware affect the software programmer as well as the hardware designer. And we've already been talking about trade-offs. I think thinking critically is most important, frankly, hopefully. And feel free to keep asking questions like you have been. Think critically and let's have a discussion on these topics. And hopefully, I think this is important also because not a lot of courses do this, in my opinion, not enough courses, let's say. Thinking broadly across the levels of transformation, across the computing stack. I think that's a lot more important going into the future than it used to be before. It was always important, but like the early system designs were hardware, software, co-designs, right? In the 1950s, 1960s. And then we specialized a little bit into each direction. But I think if you want to have a big impact on system design, you really want to understand the computing stack much better. Okay, how to analyze and make trade-offs in design. This is going to be especially important in the analysis of ideas that we do, but also in the labs that you are going to work on. And hopefully apply all of the above in the several lab projects and homeworks. How many of you have started the lab and homework? Okay, that's good. Yeah, we will hopefully have some sessions, and I think Mohammed will be in touch in terms of who will be contact points for the labs, first labs and homeworks at least. Okay, I think I mentioned this before, but the goal is to really understand the principles, the precedents, what came before. So we're going to talk about other stuff that was done. Actually, a lot of things we're going to talk about will be stuff that was done, right? As I've shown you today. But based on such understanding, hopefully you can evaluate trade-offs better of different design ideas, and develop principal designs, and hopefully new designs at some point. I'm always open to ideas. So if you have some idea, whenever you're listening and some idea doesn't make sense to you, or some idea makes sense to you, but you think you can do better, feel free to discuss that. And the focus is on all of these as we discussed, right? In computer architecture, of course. Okay, I think maybe this we didn't discuss as much, but so why these goals? I think regardless of your future direction, whatever you do, I think the learning the principles and the methodical analysis techniques that we will cover in this course will be useful to do many things, let's say. Hopefully you'll design better hardware, better software, better systems overall, like hardware, software, co-designs. Hopefully you'll make better trade-offs in design. Hopefully you will understand why computers behave the way they do in a much better way than you did before. And I mean, these are all related to computers. Maybe making better trade-offs is not just restricted to computers. But in general, I think the techniques that we will use, like the trade-off analysis, methodical analysis, critical thinking, will enable you to solve problems better, because a lot of these trade-offs are happening in life also. I'm going to give you an example, I think, at some point. I don't know if it's in this, it's in the next part of this lecture, from real life. A terrible trade-off that's made in Zurich airport. I'll show you the example later on. Especially in COVID times, it's a bad idea. But you'll see what I mean maybe later on. Hopefully this will enable you to think parallel, because in the simulator that you develop, for example, I think computer architecture is really all about parallelism. Parallelism is a big component of it. We'll talk about computation memory, for example. We'll see how it exploits parallelism in the cells of memory, for example. And think critically. And who knows what else, right? Hopefully. Yeah, another thing I want to mention is this course, I mean, computer architecture, somehow people think that it's computer hardware, but I don't believe that's the case, basically. You will be much more capable if you master both hardware and software. Computer architecture is really at the hardware-software interface. And I think it has implications on both hardware and software, as we discussed in an earlier lecture, right? And I think if you take it that way, like hardware, software, and spanning across the system, you can really develop better software if you understand the hardware. And you can design better hardware if you understand the software, right? It works both ways. And you can design a much better system if you understand both, actually. And that's what's happening exactly today. Even in industry, finally, let's say, industry is designing better computing systems today. All of these accelerators that we gave examples of, they're really hardware, software co-designs. They didn't say, okay, I want to design better hardware. They didn't say, I want to design better software. They said, I want to design a better system. And that's going to be increasingly important into the future. And again, in the end, your goal is to solve the problem, right? Your goal is, well, it depends on how you specify your goal, but in general, the goal in computing is solving a problem. And solving a problem has nothing to do with just designing the hardware, just designing software. So solving the problem is really solving the problem. If it requires designing the entire system, so be it. Okay, and that's why we take this expanded view. Okay, what do I expect from you? Hopefully, you already have some background in digital design. It shouldn't be digital circuits, actually, some sort of computer architecture course, digital design. How many of you have not taken a computer architecture course? Don't be shy. Okay, that's good. Maybe it's not the same computer architecture that I teach, like in digital design and computer architecture, because we come from all varied backgrounds. How many of you have taken the digital design and computer architecture course? Okay, very few people. Maybe they're online because people have been used to being online in the last few years. Well, 2 years, let's say, in the last 2 incarnations of this course, of that course. So yeah, I will ask you to study some of those materials if you're missing some background. But I think it should not, if you've taken some general computer architecture course, this will not really, you will figure out how to actually solve, do the assignments, for example, hopefully. Okay, what do I expect? I think most important thing is having an open mind and being willing to take in many exciting concepts and analyzing them. Hopefully you'll learn the material thoroughly. I mean, there will be a lot of material. And I think learning it is important, but you don't need to learn every single detail of the material, right? There are important things, there are not so important things. Important things are really the trade-offs and the ideas and the concepts. Not so important things are exactly, I don't know, for example, the bit error rate in RowHammer, right? That's not so important, right? The important thing is there's enough errors that are caused to affect system security and reliability, let's say. So I think it's important for you to also develop methods of distinguishing between what's important and what's less important. And again, almost always concepts are a lot more important. Concepts, ideas, trade-offs, their implications are a lot more important than numbers in general. That's why Hamming said the purpose of computing is insight, not numbers, right? So it's insight in the end. Okay, I would suggest, I mean, there's nothing required in this course in a sense, right? Clearly, I mean, I never require people to attend my lectures, even in undergraduate courses. It's all about you deciding what you attend, but I would suggest making the most out of it. So attend lectures if you can, do the readings. There will be readings, and a lot of them will be, as I said earlier also, what is that? Extra credit. So feel free to do any of them. Again, it depends on your time. And basically, you don't fall behind if you don't do some of them, let's say. If you think, basically, you don't get unfairly disadvantaged if you don't do any extra credits, let's say. But if someone has the time to do it, they will do it, and they will improve their own grade without affecting others' grades, let's say. I think that's the beauty of this sort of course. Okay, doing the exercise, doing the labs. And as I mentioned, sometimes you probably know, well, as you read Hamming's work, learning your weakness is a good idea so that you can prioritize between these different assignments if you would like to. I think this will be a hard but hopefully fun and informative course. It's not as hard as before. It used to be harder, let's say. But I think there's a lot more extra credit material right now. That's by design, let's say. So that it enables you to actually put as much as you want to, let's say. Okay, asking questions, I mean, taking notes, up to you, of course, but asking questions is a good, very welcome, basically, in this course so that we can have more of a discussion. I mean, in the end, yes, I have a plan in terms of what material to cover, but we don't also have to cover everything, right? We can reduce some of the real content and have a discussion because that also has its own value. So feel free to ask questions. I think that's something that I cannot plan ahead, right? If you don't ask any questions, I'm going to cover the material. But if you ask questions, there may be added value that is not anticipated when I'm preparing what I plan to cover, right? Okay, hopefully you can assign, especially the required readings, I would suggest that you do. Again, it's not, even though it's called required, nothing is required. You can always not do a required reading and do extra credit readings and still get the same grade, let's say. Okay, participating online would be nice, but I guess lectures online and in person. I don't know how many people use Moodle. Yeah, okay, you're using it. Is there a discussion on Moodle right now? Okay, I'm not sure. Yeah, I'm not sure. I don't like the Moodle interface, but if you like it, that's good. I'll try to be on there also. Start early. So this is, I think, some advice in terms of finishing the assignments. I think starting early is always good. You don't want all of the assignments to be accumulated. Basically, you want to be making the trade-off of what assignment to do or not to do as things go, as opposed to accumulating everything to the end and doing all of the assignments at that point, right? That's not a good condition to be in, let's say. Yeah, and there will be feedback, so come to the office hours, discussion sessions, etc. And as I mentioned, go to the TAs that are specialized for each lab and homework. Okay, this is a quote that I like from Pasteur. I may have said this earlier, but chance favors a prepared mind. In general, not just this course, of course. In general, if you're prepared, you can be ready to invent new things. So there's no such thing as luck, right? As Hamming also says, right? Luck is visible if you're prepared. So you may actually have a great opportunity, but because you don't have a good background or preparation, you may lose that opportunity, right? Because you have no idea how to take advantage of that opportunity. Whereas if you're prepared, if you've done a lot of readings, etc., you may actually see some observation and say, oh, okay, there's something big here, right? And then maybe do something big. Okay, I think preparing and managing your time, I mentioned this, so I would suggest, again, there's no deadline in terms of labs until the end of the semester. So you can pace yourself, but I think it's better not to delay them. Okay, I think I'm going to, maybe I'll mention this. Hopefully the trade-off analysis we make will hopefully change how you look at and think about the designs around you also. I always become fascinated when I can, let's say, correlate some architectural concepts, computer architectural concepts, computer concepts to what I see around me as well. Okay, so I think we discussed this before, but this is the distribution of how you will be evaluated. Lab assignments are half of the course. So there will be 5, so each of them is 10%. I think there will be 5, right? Unless I'm mistaken. Okay, good. We may have 1 extra credit, but I don't remember. Anyway, we'll adjust it also depending on how things go. Final exam is reduced from 35% last year. This keeps reducing. It used to be 40% initially, I think. Now we're down to 30. That's good. And homeworks are important. Homeworks are basically for you to learn the material. Some of the homeworks, I mean, the solutions are online, actually. I will tell you that right now from the past. Well, most of the questions are going to be similar to past homeworks from the past courses. So the solutions are online. But of course, if you just copy and paste the old solutions, you lose the opportunity to learn. I would suggest doing it yourself, basically. Okay. So there will be many extra credit possibilities in all of these, actually. So I would suggest taking advantage of them. Okay, let's see. Any questions so far? Yes, please.
The reviews are part of the homework.
Yes, they're part of the homework. But I mean, there are many extra credits, so you can actually get, I don't know, even though homeworks look like they're 20%, if you do all the extra credits, maybe they really account for 40% or whatever, right? You will see that. Sure. But reviews are officially part of the homework. Yes. Required reviews are definitely part of the homework. Okay, course goals. I think this is clear, but maybe I should reiterate them. Hopefully, we'll familiarize you with both the fundamental operation principles and design trade-offs of processor, memory, and platform architectures in general in today's systems, focusing on the important topics. And again, like my other courses, there's a strong emphasis on fundamentals, design trade-offs, and current and future issues. And since this is an advanced course, we'll talk a lot more about current and future issues. But again, fundamentals don't go away, right? Even if you're talking about current and future issues, fundamentals are always there. And as we discussed in an earlier lecture, like we need to look, as an architect, you have to have eyes everywhere, right? You need to look backward, forward, up and down in the technology stack, and also software, and also backward and forward in the future. And so basically you need to develop that skill, hopefully. And I think the second is really simulation labs. Most of them are simulation based. Actually, all of them are simulation based. And you will use different kinds of simulators also. So hopefully you'll get a good background and experience on how to design, implement, and evaluate a modern processor or different components of a processor, I should say, by performing hands-on simulator implementation. And we'll have a lecture on simulation, hopefully, where we will discuss the trade-offs in simulation also. We decided that it's important to have this high-level simulation. For example, in digital design and computer architecture, you did FPGA implementation. It's very low-level simulation. In this course, we're taking the abstraction level higher so that you actually do high-level simulation, C-level simulation. Clearly, there's a trade-off between those two, as we will discuss. But this sort of C-level simulation enables you to explore many more techniques than you could otherwise do, right? You cannot implement everything in hardware. You cannot implement everything in RTL, but in software, high-level software, you can implement many things and explore them. Okay, functionality is important, and hands-on design, implementation, efficiency. Maybe we'll have some competitions in some of the labs also. But the labs will have extra credit also, as you have seen probably from the first lab. Okay, so making things worse is important. That's real, right? You need to make things work. Okay, any questions on this? Okay, so course website, probably you're familiar with it. Everything is posted there. I think we keep adding announcements. We keep adding links to the videos, for example. But you can also find them on the YouTube page. And probably many of you have done. How many people have not done homework 0? Okay, that's good. It was due, but again, we can be flexible in that deadline. We're flexible with many deadlines. Yeah, I think homework 1 is already out. Lab 1 is already out. I think they're due soon, right? Oh, is that homework 1? Oh, lab 1 is due tomorrow? Okay. Yeah. Well, I think that's because we, yeah. Again, lab dates are really, you don't lose anything basically if you don't finish it tomorrow, right? That's the point. Yeah, you can submit it. I think maybe Juan can correct me, but I think January is 30th or so, something like that, right? Yeah. But again, I wouldn't recommend delaying it basically for your learning experience plus, yeah. But yeah, that's the idea. Homeworks, I think due dates are going to be less flexible. Is that correct? Well, yeah, because we're going to release the solution to a homework. But again, as I said, homeworks are for your learning experience also. And yeah, reviews, I think with the reviews, we're going to be very flexible. So
reviews, we are flexible.
Yeah.
You will be able to submit reviews until the end of the semester, assuming that the end of the semester is end of January or first week of February. That's the same for the labs. For the labs, the goal is to give you feedback as soon as possible so that you keep improving your work. For homework, it's not like that because it's better to release the solution because they will be also important for the preparation.
exactly. Yeah. Okay, cool. Yeah, again, website has a lot of information. And again, I think my perspective is that my goal is really for you to learn in this course and grow in this course. So I think a lot of these assignments are relatively flexible, as Juan explained. Homeworks have a particular reason why we're not as flexible, but again, homeworks, hopefully you even if you don't submit a homework, for example, you can make up all of that by doing extra credit assignments and reviews. But I would suggest still doing the homework so that you can actually, a lot of the homework questions are past exam questions, for example. They will help you in the exam in the end. Or they will help you learn also, because there's a lot of the homework questions are interesting questions, I think. Some of them are puzzle-like questions. They will enable, some of them are reverse engineering questions, for example. And I think reverse engineering questions are the best in terms of testing understanding of a concept. Forward engineering is usually easy. You may understand some concept enough to do forward engineering, but reverse engineering is usually harder. It may require a deeper level of understanding of something. So I'm a big fan of reverse engineering in general from that perspective. Okay, but in the end, the goal is really for your learning and growth. So especially since it's an advanced course. I mean, this is my general approach to education in general. It should really be about learning and growth as opposed to stamping grades, let's say. So my goal is not to just stamp grades, and my goal is to enable you to learn and grow. I understand that grades may be important to some of you at some level. I guess in master's level courses, it's less important, but if you're a bachelor student taking this course, it may be important, that's fine. Yeah, different people place different importance to grades, but you will have a lot of opportunities to learn and grow at the same time, get good grades, let's say. Okay, but please know yourself and plan accordingly, basically. Don't stuff everything to the end. I think that's what Richard Hamming also says, right? How many people have done this reading so far? Okay, great. Most people, I see. Okay, excellent. How many people have watched the videos of Richard Hamming? Okay, you have watched the videos of Richard Hamming? Okay, wow. Do you like them? Cool. It's okay. It's a good lecture series, I think. Oh, all the videos, yeah. Oh, just the video. Okay. Did you replace the video to as opposed to doing the reading? You did both. Okay. I wouldn't recommend doing that because the lecture was delivered. This reading is a transcript of a lecture delivered in 1986, and this particular video called "You and Your Research" is actually from 1995. And he has a different, I mean, even though the fundamentals are the same, it's not the same content, let's say exactly the same content. In fact, that entire lecture series probably covers all of the content in You and Your Research, maybe not everything, but clearly that lecture series is a whole semester, right? You don't want to be watching it in one day, let's say. Yeah, but I would recommend all of those lectures. They're actually quite good in terms of setting perspective. And I think Hamming has a great perspective, frankly. And these are some things, as he also says, some things that you don't get in regular courses, right? Okay, I will also suggest this talk as I mentioned in the past. Okay, any questions? Yes, please.
Just a general question. Can you tell us how many students are enrolled in this class actually?
Could you say it again?
Do you know how many students are enrolled in
how
this
many
class?
students are enrolled? Yeah, that's a good question. I didn't really check. I think when I checked last time, it was 50 or so, but I didn't check recently. I think it's still 50. Why? Okay, yeah. How many students are attending? Yeah, I think not. Yeah, not clearly not the majority is here. Yeah, maybe there are some people online. Maybe people are looking forward to watching it later. Or maybe they're never going to watch it. That's also fine. All of those approaches are fine with me. As long as you learn and grow, I don't care what approach you take, basically. Does that sound good? Yes, there's one more question in the back.
You mentioned something about, I think, sessions where we're going to discuss the labs. Did I understand that correctly?
Yeah,
How
that's
is that
going to
going
be. So I think there could be multiple things. Certainly, there are office hours you can go to. But we'll try to also have sessions, special office hours, for example, and maybe some of these sessions where we discuss the labs as well. But if you don't have that sessions, for example, and if you need help with a lab or if you want to discuss it with some TA, please go to the TA who's responsible. Go to their office hours or contact them directly. Does that make sense? Okay. Yes.
One more question. What kind of collaboration is allowed between students? Can we just discuss questions? Can we look at the codes?
Yeah, I think. I mean, I'm relatively relaxed about it. So if you want to talk, so I think the lab you submit should be all your own work. Okay, you cannot just copy code. So plagiarism is not allowed clearly. But you can discuss the content of the lab with other students and say, okay, this is the approach that I'm going to take. What are you going to do? Something like that. So that sort of collaboration is fine with me, frankly. As long as it's your, so basically I will not monitor, I will not have a strict policy saying, okay, you cannot talk about it. I think that's not good for your growth, for example. But if it helps you do the lab better, sure, why not? Yeah. That's true for homeworks also. Again, homework solutions are mostly on the on previous year's websites anyway. If you discuss them, it'll be better for sure. Yes.
Do we already know when the exam is taking place? Is it end of semester or like in the exam session?
Oh, so it's going to be end of the semester sometime. We haven't decided the exact date, but sometime I don't remember when. When was it last time?
Last year it was the last day.
Okay. Yeah. Yeah, it could be a similar time basically, but we will discuss that. It could be it would be during this session, for example. One of the sessions will be dedicated to the exam. Yeah, yeah, we don't want to linger to the exam session. Okay. Does that all sound good? Okay, then I will try. Is there a question on chat? Verilog. Oh no, you're not going to use Verilog for the labs. Not for. It used to be. Maybe the website is a bit stale. Maybe you can take a look at that. Unless I'm mistaken, there is no Verilog in the labs anymore, right? Yeah, we used to have Verilog in the labs, but not this time.
In case, for example, you want to take a look at labs from previous years.
Yeah, yeah. Okay. Any other questions? Or should we start the next piece? Oh, where did it go? Very interesting. So when I share my screen, okay, it came back. Okay. Yes, please.
You mentioned that this year's iteration of the course will be somewhat easier than the previous years. Like what about that makes it? What about this year's iteration makes it easier?
Well, sir, maybe I should say it this way. There will be more extracurricular assignments that enables you to do more. So I think we'll have. Yeah, I think that's the best way of putting it. And also, there's less emphasis on the exam, right? There's more emphasis on the labs. Probably that's it. But hopefully we'll have more discussion. Like last semester, well, not last semester, last incarnation, because it was fully online, we didn't have a lot of discussion. Right now we're in hybrid, and this sort of interaction was less possible in fully online mode, basically. I don't remember having a lot of discussion. There were still a lot of questions. We answered them, but it's not the same thing, let's say. Yeah, I don't think so. I think course material will be similar. It's just you will have more opportunities to manage your time better based on the extra credit that you can do. Does that make sense? Okay. And maybe we will also cover less because we'll go slower because there will be more discussion, right? I should also say it. Maybe we'll not be able to cover as much material, but that's okay, I think, as long as it's useful. That's my guess, in fact. Okay. We have about 12 minutes. Should we start or should we delay it to tomorrow? We can start. We may not be able to finish. Okay. Okay, maybe we just start. Okay, I guess let's start. Since many people voice start, I guess we should take a vote. How many people want to start? Okay, how many people don't want to start? Don't be shy. I won't be offended. I won't be offended even if you leave, you know. Yes. Oh, do you want to start? Okay, you don't want to start. You're voting. That's fine. I think you're outvoted. Sorry. It's not my fault. I would probably vote for not starting also, given that I'm not going to finish it, but I will start. Okay, so let's start, I think. We're not going to finish it, but at least I will give you the background and maybe we'll stop at a point where it makes sense. Okay, I mean, this is going to be an example of what we have discussed earlier. Clearly, we talked about levels of transformation, right? This is an old slide that I'm not going to cover. We talked about the power of abstraction, levels of transformation, enable abstractions. Basically, you just need to know the interface between different levels as opposed to what happens underneath or above you, right? So abstraction is good for productivity, as we discussed, right? Because you can just focus on your level and just know the interface. But if you have a problem, this breaks down basically. You need to break the layers if you have a problem. And today we're having a lot of problems, as we discussed, right? If you want to design a much more efficient and higher performance system, you need to break across the layers and design across the system. And we've discussed this slide earlier, so I'm not going to repeat it. There may be many, many problems that you're having, and you may need to cross the layers at that point when you have problems. So I think today we're in the general mode of we always have problems. That's why I think this understanding what goes on above you and underneath you in the layers is really important. Okay, I've already mentioned this also. There are 3 key goals we have. I'm not going to talk about that, but clearly these goals are really about crossing the abstraction layers. So we'll see an example of why. This is one of my favorite examples. This is some work that I have done right after my PhD when I was at Microsoft Research. And we wanted to look at multi-core systems and the problems caused by multi-core systems at that time. And this is an example of crossing the abstraction layers, in my opinion, because the problem can be solved at multiple different levels and layers. So this is a multi-core system. It's an old one from 2006, I think, AMD Barcelona. It's only 4 cores. It looks beautiful still. You can see the cores here. L1 caches are inside. You can see the L2 caches. You can see the shared L3 cache shared between the cores. L1, L2 caches are private, as you can see, to the core. DRAM controller, memory controller, and the memory interface, and clearly the memory chips, memory module in this case. So we're going to examine actually almost all of these components. I'm skipping the caches. You're doing the labs and learning the caches over there, but we're going to focus a lot on the memory system, as we discussed. And this was a trend. Like when we were looking at multi-core systems, there's a reason for it clearly, because scaling of single core performance and power became very difficult. As a result, industry decided that they would put multi-core systems, basically have more cores in a single chip, right? And this is clearly simpler and lower power than a single large core, right? Because you can build simple, lower frequency cores and put them together. And you can actually enable parallelism that way also. You can get parallel processing on a single chip, which could lead to faster and new applications, right? That was the hope, right? Of course, software is not easy to move. People had a lot of difficulty parallelizing their applications. But one good use case of multi-core systems has been putting multiple applications at the same time. For cloud computing, for example, you can have a server with 100 cores, and you can execute 100 different applications from different users, right? That sort of parallelism is easy to harness, let's say, compared to taking a difficult parallelized application and parallelizing it across multiple cores. Okay, and clearly we've seen recent multi-core systems. I've shown you some of these, right? And they're more complex than the earlier multi-core systems that I show you in this picture. And I'm going to repeat what I showed you earlier. Okay. Yeah, it's fascinating to see how things have evolved, right? Right now we have many, many cores. You can see some of the numbers over here, for example. IBM Power 10, I think has, yeah, you can see that's 15 to 16 cores, 8 threads per core. I think 15 to 16 because one of them may not work sometimes. Yeah, I think in their presentations, they say 120 threads, which is 8 times 15. So I think maybe they use that, they don't describe exactly what they do. If maybe they have a new article where they describe what they do, but they may either take it offline or use it as a service processor or whatever. It's interesting. Okay. Okay, so clearly there's a trend, many cores per chip. Ideally, what you want is n times the system performance with n times the cores, right? That's nice scaling, linear scaling of performance. And performance can be measured in terms of multiple applications performance. I'm not going to talk about parallelizing a single application at this point. We're going to talk about that later on in the lectures, but at this point, let's focus on running multiple applications. If you're on multiple applications, you should, if you're on n applications, you should get n times the throughput, right? What do we get today? So that's the question we asked in 2006 or so, basically. And this is one of the measurements that we did on real multi-core systems of the day. Those multi-core systems of the day were really simple, 2 cores. And this is a real measurement on one of the Intel systems. We ran these 2 applications, MATLAB and GCC. And we measured the slowdown. These are single-threaded applications. We measured the slowdown each application experienced compared to when it's running alone on the same system. And you can see that MATLAB slows down by only 7% when it's running together with GCC. And GCC slows down by 3x when it's running together with MATLAB. Make sense? I mean, this is a measurement. There's nothing to argue about it. As long as you're doing the measurement correctly, this is what you get. And this was reported in this paper, basically. And we were kind of surprised. Well, we were kind of expecting it because we knew how the memory controller is designed. But when you actually make MATLAB low priority and GCC high priority, this doesn't change because the operating system has only 2 applications to schedule. The operating system schedules MATLAB and GCC. And basically, it's assuming that those are running nicely in the course. And we call this a memory performance hog because it's slowing down the GCC application because of memory interference, essentially. Okay, maybe I'll ask you questions sometime. So I guess these are rhetorical questions at some level, but can you figure out why the applications slow down if you do not know the underlying system and how it works? I guess maybe I'll ask you the question, why is this happening? I kind of gave you hints already, but why would you see this sort of slowdown when you're running 2 applications on 2 different cores? Exactly, it's accessing some shared resource, right? Do you know what that resource is? The memory, okay, thank you. Yeah, the memory. Essentially, in this case, it's the main memory, actually. But again, if you really want to understand, you really need to understand the system. Right? It could be the cache also. Maybe MATLAB is trashing the cache of GCC, trashing the cache contents of GCC, such that GCC is always going to memory, right? But that was not the case in this case because we didn't have shared caches between the cores at that time. Because it's not being affected. I mean, it's being a little, but it's the hog. Yeah, that's the next question, basically. Yeah, we'll see. That's the purpose of this discussion. But you're asking the right questions, basically. So why is there disparity in the slowdowns? And the answer is there's some interference in shared resources. Why is one application being slowed down much more than other? Now, let's see. It could be that, for example, MATLAB doesn't benefit from cache. GCC benefits from cache, but MATLAB has a lot of stuff that it streams through the cache, right? It could be evicting the useful stuff for GCC without benefiting from the cache, right? That could be the reason, right? But cache is not the problem here. But if cache were the problem, that could be the reason, for example, and we will see that later on also. Okay, so these are rhetorical, as I said. Can you figure out why the application slowed down? Can you figure out why is there a disparity in slowdowns if you do not know how the system executes programs? And can you fix the problem without knowing what is happening underneath? And I will argue that all of the answers are no. You really need to know what's happening underneath. If you only know about software, say, oh, I'm writing MATLAB, and I hope it executes fine. And you get this, well, I'm writing GCC, sorry. MATLAB is okay in this case. I'm writing GCC, I hope it executes fine. And you get this problem, and you have no idea what's going on, then you're stuck, right? That's my point, basically. That's why you need to cross the abstraction layers. Again, if you're an operating system designer and you see this problem and you have no idea what's going on in the underlying hardware, again, you have the same problem. Right? That's why we need to know what's going on underneath. Okay, if I rephrase the question, why is there any slowdown? I mean, maybe you should not have any slowdown, right? So if there's no resource sharing, there should be no slowdown. So, okay, right. Why is there a disparity in slowdowns? Because there's some unfair resource sharing, clearly. And how can we solve the problem if you do not want that disparity? Now that opens up a lot of interesting directions, clearly. So I think before I go into more detail, why is this even important, right? So we want to execute applications in multi-core systems. We want to consolidate more and more. And this leads to higher efficiency and higher throughput. Cloud computing is one example, mobile phones, automotive systems. In fact, there's a push towards automotive systems consolidating a lot of running pieces into a single big multi-core system, single big chip, so that everything gets processed there. This may not be very good if you have this sort of uncontrolled slowdowns, right? You don't want an important machine learning accelerator to slow down because somebody is watching a DVD in the back of your computer, car, right? That will not be very good. Okay, so basically these issues arise whenever you consolidate multiple applications. And you want to mix different types of applications together, and these could have different quality of service guarantees, like pedestrian detection, which could be a machine learning accelerator, video. It depends. Of course, some of the guarantees need to be really hard guarantees, and some of them are software guarantees, and some applications don't even have any requirements, right? And there could be, I think I already said this basically. So you really want the system to be controllable and high performance. Basically, even if there's some resource sharing, you would like to be able to control the resource sharing and also get the benefits of consolidation, right? Okay, now let's take a look at why there's a disparity in the slowdowns in this particular case. And I'm going to cover part of it, but not continue a lot, I think. So this is the system we examined. So whenever you actually have this result, you should first look at the system. What does the system look like? This was our system. I think Intel something, I don't remember. Intel Core Duo, Core Duo, I think. It's somewhere in the paper. But basically, caches were not shared. There's some sharing in the interconnects that we don't know exactly what. And there's certainly sharing in the DRAM controller. So DRAM system is shared between the cores, but caches are not shared. So this is what happens basically. MATLAB and GCC, they both access the memory controller, and MATLAB happens to be very intensive, meaning it generates more requests per second or per nanosecond, let's say, compared to GCC. It's a very heavy application from the memory's perspective. And memory controller was doing this basically, prioritizing MATLAB for a long time. As a result, the poor GCC single request was waiting. And GCC has only one request, let's say, once in a while. It's not very memory intensive, but that request keeps getting delayed. As a result, GCC loses performance a lot compared to when it's running alone on the system, right? That's the idea. There's some unfairness in the memory controller. The memory controller is not really aware of the different requests coming from different applications. As a result, it's optimizing for something, and we will see what that something is, which is really memory bandwidth. It's trying to maximize the memory bandwidth, as opposed to trying to fairly service the different applications. And that's the cause of the problem, basically, in this case. So if we dig deeper, let's see, how much time do we have? Do you want to stay longer, or? Maybe not. Maybe this is a good place to stop, actually. Maybe this also lets you think of why this is happening. So what's being optimized here? I think that's where we will start tomorrow. So certainly there's some unfairness in the memory controller, but why is the memory controller causing that unfairness is something that we will look at, because there are multiple aspects of it. One is the scheduling policy over here. Well, the main culprit is the scheduling policy, but it has multiple components. It's really prioritizing older requests as well as some requests that have good locality in DRAM. So to really understand what's going on, you really need to go deeper into how the memory banks are organized. And that will give you why the design decisions are made the way they are and why they're unfair when you're running multiple applications in the system. So I think to actually to be fair to this topic, we should stop here and we can continue tomorrow. So tomorrow we will finish this part and hopefully we will start the data retention, which is a key scaling issue in main memory. Okay, any questions? I guess people in Zoom also say tomorrow. That's good. Okay, then we're done for today. I'll see you tomorrow. Take care. I haven't heard that in a while. Even if you did it on Zoom, it's hard to hear on Zoom, I guess. Okay. Let's see. I guess